This afternoon is going to be a little bit different because we have 6 of the LOIC's graduate students to talk about their work this afternoon. So what we're going to do is give each of them a little introduction, and then they will present for about 15 to 20 minutes on what the work is. And then we'll move on to the next presentation. We'll take all of the questions at the end during the panel session and Q&A. So feel free to write any questions that you have in the Q&A box as they're coming along. You may want to specify which of the speakers you want to address a certain question to. You don't have to, but you can. And at the time, you can also use the raise your hand button to request to be unmuted to do questions then. So to begin, we have Jesse Moro dos Santos. He's a forest engineer that graduated from the Federal Rural University of Pernambuco in Brazil. I hope I pronounced that okay, Jesse. Oh, good. He used to work with tropical dry forest dynamics to understand how tree growth responds to prolonged drought. Now his master's thesis focuses on the annual growth response of range-wide populations of Acadian tree species in climate using provenance trials. So he's going to use dendrochronology to match annual ring widths with corresponding historical climate conditions to identify populations with good growth performance and local adaptation. When he's not working on his thesis, Jesse enjoys playing board games, taking photos, exploring new places, and enjoying the outdoors. Take it away, Jesse.
Hello, everyone. I'm going to share my screen with you. So can you see my screen?
Yes, we can.
Okay, so as Patricia said, my name is Jesse Moura dos Santos. I'm a Master of Science in Forestry candidate at the University of New Brunswick. And I'm going to talk a little bit about my thesis that is mainly about red spruce. And the title of my thesis right now is Sensitivity of Red Spruce Provenances to Projected Warming in Eastern Canada. And I'll bring a little bit of introduction. So red spruce is a keystone species of the Acadian forest. You probably know red spruce, and it has a really high economic value for the forest industry. But red spruce growth and this distribution had a stark decrease during the 60s and 90s, mainly during this period. And after this period, it kind of recovered. Some research says that it recovered. Some of them say that it's still recovering. But the decrease happened because of winter injury, atmospheric pollution, and land use history, and also some of those factors together. And after that, as I said, it came back. It's kind of recovering, but it's uncertain. Like there's a lot of uncertainty of what it's going to become of red spruce. So with this, we have some predictions that says that red spruce is going to respond negatively to the climate change. But we also have some predictions that say that for the next 20 to 40 years, red spruce is going to have positive response to climate change, but by the end of the century, it's going to be mainly negative response. And we were probably going to see the red spruce distribution reduced by the end of the century. And to avoid that, we have to look for some strategies. And some of the strategies that we have that we can try to make red spruce have a positive response to climate change, it's assisted migration or pre-commissure thinning. And as you might be aware, pre-commissure thinning, it's a silviculture treatment. So it might help to have a positive response in terms of growth, but in terms of distribution and abundance, it might not be the best option. So an assisted migration can be that option to help the distribution and abundance of red spruce to continue or have a positive response. And for those who don't know what assisted migration is, I have 3 different types of assisted migration here in the figure in the right. So if you look at the APM, it's assisted population migration. And when I talk about assisted population migration, I'm talking about moving a population from a place to another inside of the range of the species. So let's talk about red spruce. So, if I'm talking about population migration, assisted population migration of a red spruce, I'm taking a population of red spruce that is inside of its range, so red spruce from North Carolina, and moving it to a place that is still inside of its range. So moving it from North Carolina to New Brunswick, it's inside of the range. Another assisted migration is the ARE. So it's assisted expansion. So it's when we are expanding the range of the species. So it means that we're moving a population from outside of its range, but that range, it's just connected. That the place that I'm moving is connected to the range. So it's like I'm just expanding the range. So if I would say, let's say we're moving red spruce from outside of its range, but I just want to do an expansion, I would move it a little bit further to Quebec. I know we have some in Quebec, but it would be a little bit further. So that would be an assisted expansion migration. And the other one would be assisted species migration, where we move a species from its range to outside of its range to a place that it doesn't really have that species. But in my case, my study, I'm focused on the APM, the assisted population migration. I'm trying to see if there is any population from south or north inside of red spruce range that might be adapted to climate change, that might have something that can help us to have a positive response in terms of climate change. So with this, my objective is to compare the climate sensitivity of different red spruce populations by revising 60-year-old plantations from different origins distributed across Eastern Canada. And my two main hypotheses are sensitivity to climate moisture indexes increases in drier sites, indicating some level of water limitation, and that red spruce populations displays a trade-off between cold hardness and growth response to warming, with cold adapted populations showing lower growth in hotter sites. So to do that, we used two set of plantations, two different studies that were established by the Canadian Forest Service back in the 60s, 1960. And those two studies, the difference between them, they're both plantations, but the difference between them is that one is called range wide, and this range wide, as the name says, it has populations from all of red spruce range, so from North Carolina to New Brunswick, Nova Scotia, from all of its range. And the Maritimes, as the name suggests, it's just populations from the Maritimes. We might have one or two populations of outside of Maritimes, but the main focus of the Maritimes was to have populations and the plantations inside of the Maritimes. So as you can see in the map here, in the figure 1, all the trials or the plantations were for Maritimes were just in the Maritimes, but it was also included in Newfoundland. And the range wild, we had them in Quebec and in Maine, or actually New Hampshire. And so in the figure 2, you can see some of the populations that we got, that we included. So as we had two different studies, we decided to work with with those two, and we decided to take 8 provenances, or 8 origins, 8 seed lots from each study. So we could have a mix of genetic and a mix of populations with a more representative amount. So we decided to work with 8 from each study, and we ended up with 16 provenances, and we collected a total of 800 trees, and we had a 5-degree gradient in terms of mean annual temperature. So to collect that, we we went to those plantations, we sampled those trees, we cored those trees, just like in the picture here, my friend Jacob coring a tree. So we core those trees. After we core these trees, we measure their DBH and height, and we also measure the surrounding trees, the trees around it. We measure their DBH because if we needed to include competitions data by the end, we would have that data. And after we collected the data, we went to the lab and we had to prepare those samples to be scanned. So we had to shave and sandpaper those cores. And then we used a microscope to scan those cores and measure the annual growth rings. And then after we measured those annual growth rings, we had to cross-date all measurements. So the cross-dates basically means that after I measure all the rings, I have to make sure that they have this the same information in the same year. So if I measure a core and it has the value of 2019, the other core that has the value of 2019, they have to have some correlation, because even though they're different trees and we might have some side differences in a lot of other factors, but they have to have some kind of correlation because that growth happened in 2019. And when we finish the cross date to make sure that the data is okay to work with, we create the model. So we tried different modeling. We tried different type of models, but we ended up using the Bayesian model. The Bayesian model, it's a little bit more complex model, but at the same time, it's a little bit more complex to build, but at the same time, it's a model that makes things simple. And it's a model that includes a lot of uncertainty. And some of the, in this model, the Bayesian model, we can put a lot of different variables, including a lot of uncertainties. And we know uncertainties, it's one of the biggest problems with modeling. And we have some different modeling types of model that we can include different types of variables, but there's not as much, we can't really include them as much uncertainty as the Bayesian model can. So to the Bayesian model, we use the log of BEA, so Bayesian area increment, and we use a equation, basically a model for the stand level and the model for the tree level. And in the stand level factors or variables, we included the soil. Can you see my mouse pad? My mouse?
We can.
Yeah, okay. So we included a soil variable, that field capacity moisture, and in order to take that, we took the information of soil characteristics from Canadian Forest Service, and we included also the competition index that, if you remember, I collected the surrounding trees, so we calculated an index with those surrounding trees data, and we also included a stand development variable that basically it's thinning since, like age since thinning, because we had the information as it was plantations from Canadian Forest Service, we had a lot of information. And in terms of climate, we tried summer climate moisture index and growing degree days. And in the tree variable, in the tree variable model, we tested the diameter at risk height, so the DBH. We also included the block where trees were collected. So like every time I was collecting a core, I was taking notes of the block that tree were collected, because it could help somehow. And the provenances itself. So as we had 16 provenances, we would have to include this here to have their differences if they have differences. So basically, when we put all of this together, we had, we could see the results of, we could see how much of each variable can, like they react in terms of growth. So if you see figure 1, we're looking at the DBH against the log of BEI. And this is one of the most variables used for growth model, that because the DBH is one of the best predictors or the best variables to explain growth. So as you can see, we have an exponential curve, exponential positive curve of DBH and basal area increment. And in figure 2, you can see a really interesting result of competition where we have the log of BA. So we have the growth here against the crowding index. So the crowding index basically is as bigger as the crowding index, it means that the tree has more competition. So it has either it has more trees around it, or the trees around it, they're bigger than the tree that we measured. So, and as you can see, we have a really clear linear response of growth to competition, where when the competition increases, the growth decreases. And this is really interesting because the competition data was collected in 2020, and we were like we had we expected to have some response, but not as much as we did, because we had like 60 years of growth, and we just collected competition index for the last year, so to 2020. But even though DBH and competition index explained a lot of the growth of the tree. And after we explain, like we have these results of the DBH competition site development, we remove this information from the raw data, from the growth, from the basal area increment. We remove those effects, the DBH, the crown effect, and then we got a residual. And with the residual, we compare, we test those residuals with the climate data. And when we compare the residuals with the climate data, that's what we got. So the figure here, the figure 3 you're looking here, it's the response of the species red spruce. I don't have different provenances here yet, so I'm looking for the overall response of the species. And if you don't know CMI, so from the CMI here, from 0 to -20, it means that it's dry. And from 0 to 20, it means that it's wet. So basically what we can see from this graphic here is that red spruce, it's sensitive to drier years and areas. So, and it's really like we can see a substantial water limitation, because if it's dry, so like 0, from 0 to -20, it's really like the growth here. This is the growth on the y-axis. So the growth really reduces like almost 50%. And when it's wet, the growth, it's happening just okay. It's like, it's really good. And if it's extremely wet, it decreases a little bit. But we can really see a substantial water limitation of red spruce to the CMI, to the climate moisture index. And when we looked for the 16 provenances, we were expecting, like I was expecting to see differences between those provenances, because one of them is, just an example, one of them is from North Carolina, another one is from south of Quebec. And I was expecting to see some differences. But in terms of the climate moisture index, we couldn't see any differences. So if you see this line here, if we have differences between them, we should see 16 lines, but we are only seeing one line here, basically. They're all together. So it means that they all have the same response. The growth responds the same in terms of CMI. So basically, it means that there is no significant difference in between the provinces in terms of climate moisture index. And it might indicate that there's a strong phenotypic plasticity of red spruce populations, that even though we're moving population from south to north from north to south, but they have a plasticity to adapt to that climate moisture. And in this case, in the case of moisture, if we're just going to consider moisture, red spruce populations wouldn't be a really good candidate to assist migration in terms of climate moisture. So again, I'm only talking about a few variables. Like we tried a lot of different site variables, but in terms of climate, we just tried CMI and growing degree days. I didn't bring a picture for growing degree days, but because we couldn't find any response of growing degree days against the growth of red spruce. Also, we couldn't really see anything. It was a flat line. So we assumed that there's no influence of growing degree days in terms of the growth of red spruce. So I have some key messages from my results. It's that tree size and competition has the biggest influence in growth, and that was expected. Red spruce growth is sensitive to dry areas and sites. Growing degree days does not influence red spruce growth because of the flat line. We couldn't really see any response. Red spruce populations shows a strong phenotypic plasticity. Again, in terms of CMI, in terms of climate moisture, all provinces, they had a similar response. So if, let's say, if I move seed source provenances from North Carolina to New Brunswick, we shouldn't see any difference in growth in terms of climate moisture. And because of that, they might not be ideal for system migration. But at the same time, I'm not looking at some other climate events that might happen that might have a difference between the provinces. So the decline in maladaptation of population might be related to other factors. Because if I look at when I went to the plantations, I could see some differences between the provinces. It could be due to the site quality, site condition, but it could also be because of some other variables or factors that I didn't include. So let's say adaptation during the first years of development. So when I analyzed my data, I only analyzed 40 years out of 60. So I didn't analyze the first 20 years. And some researchers says that the genetic influence in those provinces or in those populations, they show a little bit more in the beginning of the growth, so in the first years of the trees. And as I just compared the 40 last years, this is why I couldn't see any differences. But I could also, it could be, if I analyzed the 20 years, I could have found the same thing. And it would be the same. Like, so what's going on that they have differences? That could also be because of frost hardness. I didn't include frost hardness into this. But let's say if the provinces from North Carolina, it's not frost hardness, like there's no frost hardness, but the one from New Brunswick has. So there is something different, and they might respond different when we do a system migration. So this is why, this is a really important result about the climate moisture and how red spruce react to the climate moisture. But at the same time, we have to be careful because some of those factors are not included. So in terms of climate moisture, it's not ideal to do a system migration. But in terms of frost hardness, we don't know. And you're probably going to hear a little bit about frost hardness with the presentation of Storm. And that's it. I would like to thank you for listening to me. Here's my contact. You can just send an email to ask me about anything. And I can't be here for the question section. So I saw that Loic is here, so he can probably answer for me because he's doing this research with me and he knows everything about it. So if you have some questions that you want to know, like probably help you with it. But if you don't want to ask here or you don't want to ask like, just send me an email and I can help you. Thank you.
Thank you, Jesse. That was great.
Thank you.
Have fun going back to work.
Thank you. Bye-bye.
Okay, next up is James Broome. James holds a Bachelor of Science in Forest Management from the University of Cumbria in the UK, where he received the Royal Forestry Society's Viking Bursary to aid in his dissertation exploring the influence of a fungal pathogen on European ash. He then worked for New Woods Forestry Limited as an assistant forester in Eastern England before receiving a Canadian Memorial Foundation Scholarship to begin his master's here in New Brunswick. James's thesis project is investigating a balsam fir mortality event across the southern range in 2018. There are two research objectives: identify the climate anomalies responsible for the 2018 balsam fir mortality event and examine similar historic reports of balsam fir mortality, and also to isolate specific stand and site factors responsible for the variation in tree mortality across New Brunswick. When not working on his thesis, James likes to enjoy the vast natural beauty and forests of Canada, along with sampling the impressive craft beer across the Maritimes. Take it away, James.
Hello, everyone. So today I'm just going to be talking about my first chapter of my thesis, so investigating the climate anomalies associated with southern fir mortality in Eastern North America. This study was funded for an NSERC Alliance grant, and this was matched with the Canadian Forest Service funding, so I'm grateful for those funding partners. This is a balsam fir tree on the left here with southern fir mortality. This picture was taken by Dr. Anthony Taylor on my committee with Mike Levine from the Canadian Forest Service. Just an outline of the presentation. So I'll just do an overview of southern fir mortality, then discuss my data and methods before looking at the specific climate anomalies we see, and then discuss my modeling methods and the results, and then talk about my conclusion and future work planned. So really the second chapter of this thesis. So back in 2018, before COVID hit, there was this southern fir mortality reported. So it was sort of individual balsam fir trees suddenly turning bright red in early spring and early summer. So you can see some pictures here of southern fir mortality. So in New Brunswick, Maine, and also Wisconsin. It was also reported in northern areas of New Hampshire and Vermont. So the major driver of tree mortality in balsam fir is the spruce budworm. But it was unlikely this mortality was driven by spruce budworm because it takes multiple years of defoliation. And as you can see in the pictures, the foliage remained intact and just turned bright red. But the fact that this happened more in the southern range of balsam fir, so this is balsam fir's range in this figure. The fact it happened in the south and happened at the same time really made us believe that it was, climate was probably the primary driver of this, and perhaps some anomaly that was happening. So it warranted more investigation. So as part of this, I also looked at historic records, and really interesting that the Forest Insect and Disease Survey FIDS reports from the 1950s to the mid-90s, fantastic resource. But so from the 1980 to 1995, there's reports sudden death of balsam fir trees or Stillwell syndrome. Now, there was a spruce budworm outbreak in the 70s, sort of finishing in the mid-80s. So that is a factor in these 80s Stillwell syndrome reports. What's interesting is there was a couple of years that were highlighted as particular bad years, so 1982 and 1986. And that they refer to the similar description of what we've seen in 2018. So this bright red foliage observed during early summer and first noticed in late May. What's interesting about the 1986 event is that they actually produced a map. It was the only year they did this. You have lowest frequency, medium frequency, and highest frequency. So you can see to the west and the northwest of New Brunswick, you had a higher severity of this mortality. So I'll just touch on my data and methods now. So species distribution modeling is a technique that's been around for a while. It's particularly used looking at how species are going to respond to climate change. And so this takes, uses environmental and climate data and includes presence of a species. And then with this, it builds predictive models, and you can map it, your prediction of a species across a landscape. And so this was actually demonstrated in 2018 to use with dieback of blue oak, where instead of presence of a species, you had presence of dieback of the blue oak. And they used it with climate data to actually build predictive models and map where this dieback occurred. And they used boosted regression tree methods. So this is an ensemble of individual decision trees, and this was a great method to use because they were able to detect this non-linear relationship between precipitation, where you had this sort of dieback threshold, where once the precipitation fell to a certain extent, the model predicted this mortality. It's a really useful method and seemed to be exactly what we were looking for to explore this southern fir mortality event. So we needed presence data. Luckily for us, New Brunswick ERD undertook an aerial survey in 2018, as they do most years, because they monitor the spruce bloodworm defoliation. And so this map shows the blue dots here was the reports of southern fir mortality in New Brunswick. But during my proposal presentation, it was pointed out to us that reports continued to come in after this aerial survey was complete. And so to avoid false negatives, we actually excluded the New Brunswick absence, so the locations where the blue dots aren't on this map, that we removed them from the predictive model building. And because we did that, we then needed to get absence data from somewhere. So we actually incorporated Nova Scotian PI, where widespread mortality was not reported. We contacted local foresters there, and although some balsam fir trees will have died in Nova Scotian PI in 2018, it wasn't to the same severity as we saw in New Brunswick. So my climate data, we looked from March 2017 to May 2018, so the previous growing season, up to the spring just before this mortality started to be reported. We looked at monthly climate data, so this is just derived an average of daily data for each month. We had 2 kilometer resolution maximum temperature, minimum temperature and precipitation available to us from 1950 to 2018. We also had 32 kilometer resolution snow depth data from 1979 to 2018. So this figure just shows the higher resolution there, the blue, and then the coarser snow depth resolution underneath. And so I had to scale, match the scaling. So we had to reduce the 2K resolution to match the 32K resolution. So we had that climate data. So, how do you go about actually determining whether there's a climate anomaly or not? Well, you have to base what you saw in our case, 2017, 2018, to what you see in history. So using those time series that I just said. So we use this technique, the Z-score. So we took each individual raster square, we took the value minus the mean of that time series, divided by the standard deviation. And what this does is it changes the scale. So, instead of being August precipitation, 30 millimeter to 150 millimeter, you actually get the mean here, and then you have 1 standard deviation, 2 standard deviations, and so on, either minus or positive or negative. So that enabled us to define a climate anomaly, as a Z-score of plus or minus 1. So these rarer yellow or red regions. So just an example to show this. So this is precipitation in August. So you can see the scale there in millimeters. And then this is the same data but standardized. So with this Z-score, and what's really interesting about this is that, it's drier here according to the raw data, but then when you standardize it, you actually see that the Northwest was even drier than there, because each of these raster squares becomes relevant to its own individual time series, its own climate history. We then averaged the raster squares with, in those areas where we had presence of southern fir mortality. So which climate anomalies did we see? This map just shows what I mean there. So these crosses are those blue dots on that previous map, and then you can see the underlying climate data we've used. So we took the mean of that to tell us, these graphs here. So the top graph, precipitation, that dark blue dashed line. So it's actually started pretty wet in May here, before it then dropped, and it was very dry in July, and followed by a very dry August as well. Slightly wetter in fall, before some high precipitation events in January and April. Then snow depth was fairly normal. So this black line here, the 0 is the mean, fairly normal, but then you see this higher snow depth in April. Then max temperature and minimum temperature, they show a similar trend over that 15-month window, but so it was quite warm in spring, early spring and April, fairly normal summer, before a very warm fall, slightly cold December. Then it got warm again, and then dropped right down in April before a very warm May as well. So, and if you remember, in Fredericton, we had really bad flooding in 2018, which was partly due to this very high snow depth and then this sudden melting of that snowpack in May. So, I'm just going to touch on some of the key anomalies in more detail. So So this July and August drought we saw, so it was actually one of the driest July and August on record of the 69 years I had, one of the driest. And so, in balsam fir trees or any trees, you've got, a water column in the xylem. So you've got these water molecules are under tension. And as a drought increases, that tension increases as there's less of a consistent supply of water. And what this graph is showing is the amount of tension required in balsam in different tree species to cause a lethal 50% loss of conductivity. So as that tension increases, you're more likely to get air into that xylem and break that water column. And so this 50% loss of conductivity is considered lethal and known as hydraulic failure. And so yes, this graph shows this tension increasing on the y-axis. So you can see balsam firs actually requires less tension compared to some other species in this region or planted species. And so this sudden hydraulic failure, this 50% loss of conductivity was recently seen in widespread in Europe, in Norway spruce. Back they had a drought in 2018 and they had reports of Norway spruce dying suddenly, and so they found that it was this sudden hydraulic failure that was driving this mortality. So as well as that dry, July and August, we also had that warm April 2017, and this 2022 study showed that balsam fir actually transpires when it's warm enough in early spring, so those needles begin to lose water. We also saw a warm fall, and this 2012 study showed that fine root production actually increases with warmer fall temperatures in balsam fir. And both these studies sort of, serve to remind us that, as foresters, we think about diameter increment and growing timber, but trees are actually active before and after that stem is growing. And this figure on the right shows this stem radius increment on here. So this is balsam fir in Quebec. So at the start of the growing season, you actually have this stem rehydration period where it contracts slightly before it then grows, putting on that basal area, before then tailing off and the cell walls begin to thicken and you get these other functioning biological functions that happen. But yeah, so it's important to remember that trees don't just grow in the stem, there's other things going on. So lastly, we had this high April snow pack, snow depth. And so, conifer trees are dormant during winter, which is good news for them because, in the cold Canadian winters, all the water is locked up in the soil. The trees can't access it, it's frozen. But in the springtime, when dormancy begins to, trees come out of dormancy or are beginning to come out of dormancy, there's this slight vulnerable window. And we see some historic needle browning events reported in Canada. So in Ontario in the 50s and South Manitoba and Saskatchewan in the 50s, and then also in Ontario more recently in 2012. So this figure is the balsam fir on the top here. So this bright red foliage, this needle browning. And then this is, how widespread it was across the landscape. What's interesting about this 2012 Ontario event is they looked into it and they saw where in the areas where snow cover was lost in March, but then returned in mid-April, actually seemed to correlate with this needle browning they see across the landscape. So I'll now touch on my species distribution modeling results. So I've taken all those climate anomalies, I've put them into this model, and then this is some of the outputs that come out. So this is telling me this figure here, which of these climate anomalies helped explain presence and absence, presence versus absence. And what comes out on top is this drought in August, and then this warm period in April in 2017. So basically in New Brunswick, it was drier in August and also warmer in that April 2017. So in this figure, you've got precipitation previous August on the x-axis, and then minimum temperature previous April on the y-axis, and you've got the probability scale here. So this is talking about sudden fir mortality. So where the precipitation in August was fairly normal, the mean, or slightly wetter than usual, you basically had 0 probability of mortality. And then this increased as it got drier. But also you have this warm April, and where it increased in warmth in April, you also see an even higher probability of mortality up here. And then these were so I've got that model. That's kind of how the inner workings of this model. And then I apply that across the landscape to tell us, okay, well, where was probability of mortality likely? And so you see in New Brunswick, it predicts perfectly where we saw southern fir mortality. Now in Wisconsin, it did predict some areas, but and I was excited when I first saw this map, but then I soon discovered that balsam fir actually only really exists in the north of Wisconsin. So suddenly this model is not actually doing a good job, and maybe we need to look back at what, try a different technique. Now, luckily, because we'd standardized that climate data, we'd made Wisconsin relevant to itself, and New Brunswick relevant to itself, and Nova Scotia PI relevant to themselves, each raster square. We were able to include North Wisconsin, as presence, as well as New Brunswick presence, and compare that to Nova Scotia PI absence. And when we did that, the model, the important anomalies changed slightly. We had this suddenly snow depth in current April was very important in distinguishing the presence and the absence, and this warm May as well. So the prediction for Wisconsin here is here, and you can see it's doing a better job than before. Now, something really important about this approach that we've used is that it's not perfect as any modeling. Statistical modeling is, but basically it was a dry July in all of these areas. So this model, it tells it, okay, well, that dry July didn't matter in terms of presence and absence, but as foresters and scientists, we know that drought in July, will have affected these trees in North Wisconsin and New Brunswick. So we just have to be slightly cautious with interpreting the model results. This is just the prediction of New Brunswick, so doing a good job. But also we applied the model back in time. So we looked at this 1986 event because we had that map, with the highest frequency, medium frequency, and lowest frequency. And what's really exciting and interesting is you see, okay, the probability of southern fir mortality is less than the 2018 event, but it still is there. And actually we find that there's an increased probability that seems to match up with this highest and medium frequency that they saw in 1986. Now, you had the spruce budworm outbreak, so there's other things going on with the trees that died in the 80s, but it's still interesting that there seems to be a bit of a link between the 2018 event and the 1986 event. Just to conclude, we identified climate anomalies for a novel tree mortality events, the southern fir mortality event 2018, using this standardized climate data. We used a species distribution modeling approach with boosted regression trees, which was useful, but there are limitations as I've gone through. But what's really exciting is that this methodology could be applied to other tree mortality events and other locations pretty easily. So my second chapter, which I'm not going through today, but is taking this high resolution aero imagery that we have for Northwest New Brunswick for 2018, and we're going to take the forest stands that are over 60% balsam fir content, so the yellow shapes here. We're then going to undertake automatic pixel classification to basically identify these southern fir mortality trees. You can see here, really high resolution photography. And then we're going to determine the standard site types that experience more frequent mortality. So, we've seen that drought was important. So do we see that reflected in the standard site types? Were stands with higher basal area or sandier sites more likely to experience more mortality? And my references, and yeah, thanks for listening. And obviously there's a lot of people that helped me on the way. So I must thank them, and my email's there. So yeah, thank you.
That's fantastic, James. Thank you. Next up would be Gigi You Wang. However, she's not able to be with us today. Loic is actually going to speak on her behalf, but I will read her bio just so you can get a little information about her background. So Gigi started her career with a bachelor's degree in forestry from Nanjing Forestry University in China, and a master's degree in forestry and environmental management from UNB, and a master's degree in mathematics and statistics, also from UNB. Prior to starting her PhD, Gigi worked as a biologist for the Canadian Forest Service. Her PhD project aims at assessing climate growth relationships for major tree species from Eastern Canada and to detect changes in Eastern North American forest growth and productivity due to recent climate change. Furthermore, the climate growth relationship will be used to simulate future forest dynamics under various climate scenarios. When she's not working on her thesis, Gigi does enjoy, and her family enjoy, cooking and gardening.
Thanks, Patricia.
I
my
do
name-
yours again, but
No, that's fine. My name is Gigi for the next 15, 20 minutes. Yeah, she had a pretty bad cough. So yeah, so I'm taking over for her. So bear with me because I didn't prepare this presentation, although I did work a lot on this project. So I think I know the core of it. All right, I'll share my screen now. Okay. Yeah, future tree growth in the Canadian boreal forest. So actually, this work was it's pretty ambitious, and it's actually being revised in journal Nature. So it's probably going to get rejected at the end of the week or so. But we think it's quite significant work. Anyways, I'll get into it. So it's a work. It's Gigi's work along with myself and Anthony Taylor here at UNB. So yeah, the context she was bringing up is the importance of the Canadian boreal forests. Of course, you have a map in the center of the image where you see in green the world's boreal forest, and Canada's boreal forest is a major component of it in terms of biodiversity, ecosystem services, basically. Carbon is a huge pool of carbon in the boreal forest, and also economic importance of timber, etc., and spiritual values. There's all sorts of, we all know this. I'm selling this to, but you guys are all aware of that, right? And so the Canadian boreal forest you see on the lower part of the map covers really across Canada. New Brunswick is not considered part of the boreal forest, but some of the highlands up north could be considered in terms of boreal composition, etc., as an extension of the boreal forest to some extent. Right, and of course, climate change. I won't go over this, but you're aware. I mean, I spoke about this morning. There's some important warming, especially, and the warming is increasingly important as you move closer to the poles. So climate change is faster towards the poles of the Earth. So the boreal forest is actually expected to warm up faster than the temperate forest, for instance, or the Acadian forest here. And in terms of precip, there's increases expected pretty much across Canada. Increasingly important towards northeast, like you see, like Western Quebec and Northern Ontario. There's severe increases in precipitation, again, mostly in winter, although there's also some increases expected for summer. For instance, in the Boreal region of Quebec, it's around 10% increases or so. And I spoke briefly about it again this morning, but we know there's climate change is going to bring increasing disturbances, to the forest. And the boreal forest, really the natural dynamic of that ecosystem is driven by these large-scale disturbances, which is quite different from the smaller, gap phase dynamics of the temperate forest. So you have big fire dynamics, which are, more or less important depending on where you are in Canada. So drier climates tend to be more prone to fires, like Western Quebec, what we call the fire triangle, and also central Canada, where it's a major driver of stand dynamics. Also spruce budworm outbreak and other major defoliation, insect outbreaks, and also climate anomalies, droughts. There's a couple of case studies now that we've seen have pretty big impacts on the forest. And so when we look at the projections of disturbances, we see a pretty doomy future for the forest. And the only positive thing that could offset some of this increase in disturbance would be if the trees would grow faster, right? So it would compensate. If you think about, more disturbances, that means more turnover of the forest, more resets of stands, right? To the regeneration stage. But if trees can grow faster, then we sort of compensate this loss. Now, so far, the studies have not really been agreeing on what changes in growth we can expect. There's a majority of studies really, when they used forest simulation models for the boreal forest, tend to expect a pretty severe decline in growth, especially in the boreal species. Now, when we look at, for instance, satellite data, which is different from forest simulation model, this is satellites looking at certain wavelength that the forest emits, like green, for instance, what we call the NDVI index, which is an index of greenness of the forest. So if the forest is getting greener, that means there was more growth, more health of the forest. If to the contrary, it's getting browner, then there's a decline in the forest health. And so far, satellite imaging has been showing some greening in a lot of places of the boreal forest of Canada and some browning in other places. And when we disentangle the effect of fire disturbances, for instance, on that greening browning, we realize that fire is the biggest driver of the browning effect on the forest, but that boreal forests that are intact are actually getting greener in general. So there's some sort of disagreement on the research on how boreal forest is responding to the warming and how it will respond in the future. Yeah, so because the boreal forest, if you think about it, is so cold, that's the signature, right, of the boreal forest is growing in a cold environment. We can expect that warming might actually be beneficial by extending the growing season. We could also expect that increasing carbon dioxide in the atmosphere might actually increase water use efficiency of trees. So there's a bunch of different things going on. So in this study, what we did is we wanted to project the growth of boreal tree species, balsam fir, black spruce, white spruce, jack pine, white birch, and aspen. But in this case, we wanted to use a different approach than what's been done so far. So there's the forest simulation models, which is probably the best tool to project growth in the future. But some of the parameters in there about, well, in particular, future growth still need to be tuned better, I think. And according to the data, sometimes they don't match with the reality, what we see on the ground. So there's still some improvements to be done. And so to improve those simulation models, we thought about using those permanent sample plot networks of data that have been in place for like decades now across Canada, but also in the US. And so for the first time, we put together all the permanent sample plot data from all across Canada, basically, well, east of the Rockies for this project. So Alberta, Manitoba, Saskatchewan, Ontario, Quebec, etc. And also the US FIE network of plots. So all the US, Eastern US permanent sample plots. So these permanent sample plots basically field workers come in that plot every 5, 6, 7, 8, 10 years, remeasure every single tree. So you got a real portrait of everything happening within, a 400 square meter plot. So we know mortality, we know regen, we know growth. So it's a pretty accurate and exhaustive data set, and we have it for 18,000 plots. And so we use that data. We looked at growth from remeasurements, how each tree grew between two measurements. We crossed that with the climate at each plot and also other factors, competition and tree size, and et cetera, and soils. And then we applied a machine learning approach to sort of tease apart each driver of growth. And the nice part of this project is that we had, plots. So this is a map of the plots that we had in our study. And so we had plots, covering the really southern range limit of our boreal species, which is different from what's been done so far. So you see in the different colors represent different boreal ecozones in Canada. You have a bit of a Atlantic Maritime ecozone in the Gaspésie Peninsula here. But you see the density of plots is quite nice to get a good portrait of growth responses. So the results, when we fit those models, we see some general trends. So each curve here represents a different species. You have the species legend on the lower right corner of your screen. And you see, for instance, you see 4 variables. So the top left panel is the growth response in response to maximum summer temperature. So in general, the first thing we noticed was that there's no clear decline in growth with the warming for the boreal species, except maybe for that pink curve that you see. That's white spruce, showing a clear optimum. The other ones tend to sort of plateau or keep growing, actually. But that's only one driver, right? And then on the right, you see the frost-free period, so the number of days of the growing season. Now you see that, as you reach some higher growing season length, longer growing season, you tend to see some plateau in some species, like black spruce, for instance, tends to decline slightly when you get too long growing seasons. Then on bottom left, you see precip. So you have, an effect of precipitation on the growth. You see, like, for instance, in white spruce, the pink curve, that you have a gradual increase in growth with increasing precipitation up to a certain point, right? And then on the lower right corner, you have the effect of basal area of the stand, so competition on tree growth. And it's, as expected, right, a decline, right? The more competition there is, the less tree growth you have in a stand. So with that, next step was to incorporate future climate change into the model to see how trees would grow. So that's what we did. We inserted in each model the climate projections for the next 30 years. And so we had, summer maximum temperature, winter minimum temperature was in the model as well, frost-free period, summer precipitation, and winter precipitation is snow. And you have those maps that show on that screen, the historical baseline and the future on the right, projected changes in these variables. So you can get a sense of how things will change. Frost-free period will extend significantly. Summer Tmax will increase, summer Tmin as well, but precip would also change. Anyway, so we put everything in the model, and we looked at the response per eco-district. And so you have it here broken down by species. So there's a couple of things that stand out from this image. So in general, what we see is that there's a pretty large increase in growth, about up to 50% in growth in the absence of disturbances. And this cannot be underlined enough. I mean, we're not projecting, we're not putting everything in the model, right? We're not controlling for fires. We're not including future droughts or major anomalies. We're not including future disturbances, basically, right? So this is only one part of the equation that I'm showing, but you have some declines, which are the yellow areas, usually located in the southern areas, which are already warmer, or in drier areas. So if you look at, for instance, black spruce on the top right corner, you really see this nice gradient from increasing growth in the north and declines in the southern edge of the boreal. You also notice that some species do better than others, like balsam fir in general is growing pretty well according to our models. Same with jack pine, although there's some areas that are declining. White spruce is not doing well in the future, except in the wetter, eastern part of Canada, and like eastern Quebec. And yeah, so there's a heterogeneity in the species responses. Now, if we sum these information and account for the relative abundance of each species in each ecozone, this is what we come up with. So Eastern Boreal Shield is one of the wettest places of the boreal forest in Canada, and that's where you see the biggest increases in growth. On average, 80%, and this is mainly driven by increases in growth of balsam fir and jack pine, and more moderately, but still, black spruce. In the central Canada, it's much drier, so you don't see as much of a increase. There's some variations, okay? Still, the model projects an overall 30% increase in growth, but white spruce is expected to decline in that area, jack pine to increase. So there's some differences between species. And in Western Canada, in the Taiga Plains, there's still a significant increase in growth projected, although, aspen is projected to do much better than white spruce in that region. And if you look at Atlantic Maritime, this is a very small area, but it's It's quite dry. That area is quite dry relative to the other places, quite warm as well. So you see a general decline in that location. So I think that's pretty much it. I mean, just to summarize, this is for me like a nice optimistic view. It's not the truth. Certainly, there's a lot of things that we don't account for in this project, but it does provide some maybe more constrained information on the growth of the forest and the boreal forest, and how this might, offset some of the increasing disturbance impacts that we'll see in the future. Increasing fires, rapid, disturbances, higher frequency, and so far the growth impacts were considered marginal, but now with this project, it seems like it might actually make a difference. Yeah, so that's maybe a positive note for the Canadian boreal forest. And I think I'll stop there. Yeah. Oh, that's just, my way of saying that this is just an exercise. Models, I think, are pretty good. But all models are wrong, but they can be useful. I think this one can be useful in better understanding and predicting what things might change in the future. So thank you very much. And thanks to Gigi for putting this presentation together.
That's great, Loic. Thank you very much for filling in for Gigi on that one.
Yeah, no worries.
So next up, we have Jacob Raven. Jacob has always been passionate about ecology and forestry. He pursued these interests while working in positions ranging from riparian restoration to wildfire fighting. He obtained his Bachelor of Science in Forestry degree from the University of New Brunswick here in Fredericton. Jacob's currently researching the impacts of climate change-induced warming and drought on the growth of balsam fir across the entire region. To achieve these objectives, he'll utilize growth chambers and greenhouses to expose balsam fir seedlings of varying provenance locations to drought and temperature increases. He hopes that the data procured from this research will allow for a better understanding of the population and ecological shifts that climate change will have on the forests and stands within Atlantic Canada. When he isn't obsessing over trees, Jacob likes to cook, explore the outdoors, and expand his worldly knowledge. Take it away, Jacob.
Great introduction, Patricia. Let me get this screen shared here. Let me know if you guys can see this in a second. Can you see my screen?
Yep.
Awesome. That's good to know. Yeah, so as Patricia said, I'm Jacob Raven. I'm an MFC candidate at UMB. In my project the topic of my project is understanding balsam fir seedling resilience to climate change. In my committee, I have my supervisor, Dr. Anthony Taylor at UMB, my co-supervisor, Dr. Loic Durangeville at UMB, and my committee member, Dr. Mike Levine at the Canadian Forest Service. So today we're going to be going over 4 different sections in my presentation. 2 brief sections, which are going to be the introduction, where I'll be going over how climate change is broadly going to affect our forests and the scope of my project. How balsam fir in particular will maybe respond to climate change, and then my objectives and hypotheses that relate to that knowledge that I just shared with you. And after that, we'll get into our methods, which is an overview mostly of the phytotrons that my colleague and I built at the Canadian Forest Service. And we'll look at some of the climate control mechanisms that we employed within these phytotrons to achieve our objectives and hypotheses. And then we'll look at what attributes we measured and why we did that. And then for the bulk of this project, I didn't really want to focus too much on the nitty-gritty, so I wanted to get into the results and discussion. In particular, the effects of temperature on balsam fir needle damage and growth, potential population variation in climate adaptation, and then the takeaways, the most interesting part. How does that affect your woodlot? How does it affect your management of your woodlot? So to start off, as we've been saying this entire day, climate change is going to be warming up our summers. So there's a predicted plus 5.9 degrees summer warming in Eastern Canada by 2100 under the worst climate change scenario, which is RCP 8.5. excuse me. And many studies are showing that there's supposed to be significant tree growth and abundance shifts. Many model projections are stating that. There's going to be big abundance shifts and growth shifts in the Acadian forest region and in the Eastern Canadian forest region. And trees are basically shifting their composition or their abundance and their range towards areas that have more favorable habitat. Potentially for boreal species, they're going to be moving to more northern wet locations. And temperate tree species from the south may be moving further north. So that's favorable in this region for temperate tree species, and it's unfavorable for boreal tree species such as balsam fir. In this data procured by Anthony Taylor in his model results, he shows that in this forest composition in 2011, we have a 19% abundance of balsam fir and a 13% abundance of black spruce, which are two boreal species, and a smaller component of red maple, which are around 11%. But as we get into 2100, under the worst case climate change scenario, we have a 10% decrease in balsam fir relative abundance and a 5% decrease in black spruce relative abundance, with a very large increase, 20% increase of red maple abundance. So that's pretty concerning, these projections, especially when you think about balsam fir, because it's an ecologically and economically significant species in this region. Ecologically, it houses a lot of important species, and economically, it provides, it's a large contributor of volume to our mills in terms of studwood, pulpwood, and saw logs. As you can see, even in my woodlot in Sussex, New Brunswick, or my family woodlot, we have a large component of balsam fir in our woodlot. So it's important to know how balsam fir will be responding to climate change as it directly affects us. But right now, for that model I just showed you back there, there's little empirical data to support these model projections. And by that, I mean, we have these projections, but we don't have actual quantitative data showing their direct response to warming and drying in a lot of circumstances. So the implications of these changes, and the changes I mean in terms of abundance shifts and growth changes, may actually be mitigated by understanding the adaptational capacity of balsam fir. So I mentioned that we have a lack of data for balsam fir, and some of these questions that aren't answered right now that should be answered are that, are fir seedlings extra sensitive to climate change? Is climate change and their response to climate change different depending on their age? So we know from other research that seedlings can be very sensitive to changes in growing environment. And we're wondering, do fir seedlings, are they very sensitive to climate change compared to their other life stages? And the second question that's interesting is, does climate sensitivity vary between populations? Jesse had talked about this, where differing populations of species, otherwise known as provenances or seedlots, may have differing levels of adaptive capacity. And this is shown here in the figure to the right, where in figure 3, the y-axis shows the area occupancy of Scots pine in the Mediterranean forest, in the Mediterranean zone. And on the x-axis here, it's showing the years. So these researchers were trying to project how Scots pine will change in occupancy from the present in 2010 or 2011 to 2080 under climate change. So without including the provenance effect, or the difference in provenance or population variation in growth, we see here on this solid gray line that there will be a significant drop in Scots pine abundance in the Mediterranean region with climate change. But when you factor in provenance variation, the genetic variation in response to climate change, you can see here that in this dotted gray line, that the occupancy shift is going to be much less severe. So that's just a good example of showing why it's so important to include or incorporate. It's important to incorporate genetic variation in tree species when you're trying to predict how they're going to respond to any form of growing variable. So based on that, our objectives are to determine the adaptive capacity of balsam fir seedlings to warming and drying. And then secondly, compare the difference in adaptation amongst provenances or seedlots. Our two hypotheses in this project are that balsam fir will have increased biomass growth with some temperature increases, but will have significant decreases in mortality with extreme heat. And secondly, balsam fir seed sources or provenances from southern regions will be more adapted to warmer, dry conditions than seed sources from northern regions, just because of the forcing mechanisms in that region will allow it to have certain features that will allow it to be better suited for warm and dry conditions. So we'll get into our methods here. So we selected provenances to grow within our phytotrons. We selected 4 provenances, as you can see their location as to where their genetic material is from and their seeds are from on this map to the right. We have seedlings ranging from northern Newfoundland to southern Nova Scotia. And we got these seeds from the National Tree Seed Center. And our goal in collecting or choosing our 4 provenances was that we wanted to maximize the temperature gradient from where the seed sources were from and minimize other factors such as humidity of the growing conditions and elevation, just for example. So we picked these ones as Roddickton was the most north and the coldest of any of the provinces we could select. And likewise for Carleton, it was the hottest and most southern location. And then the 2 in between were just of even intervals of origin climate temperatures. So we have a temperature range of around 5 degrees for mean summer temperature max, as you can see here. So we ordered the seed and we grew around 2,000 at least, 2,000 seedlings at least per provenance, equaling 8,000 seedlings in total. And we assigned 15 seedlings per treatment group in this project. For the experimental design, we took these 2-year-old seedlings and exposed them to conditions up to 11 degrees above their provenance origin temperature. And we also exposed them at the end of the summer to an intense drought gradient, very dry conditions for certain treatment groups. We grew them in 12 climate-controlled greenhouse phytotrons at the Canadian Forest Service in Fredericton from May 1st to September 16th, 2021. As you can see here, these are the phytotrons we grew them in. Quite beautiful, if I do say so myself. That's a bit biased. And then these are the seedlings that are grown within the phytotron. So first we measured more broad scale measurements. We wanted to see like what happened. What are the very obvious symptoms or signs of response to these temperature and drought treatments? We measured the dry biomass of above ground, which would be the shoot and needles. And then we split that up and measured it independently of the roots of the seedling. So then we could determine the root to shoot ratio of each seedling. And the root to shoot ratio is very useful in determining a seedling or a tree's potential response to a stressor, where in dry conditions, seedlings sometimes allocate more of their carbon that they've generated from photosynthesis into their roots, so that they can generate or that they can gather more water from the soil. So it's a really good tool to use, a diagnostic tool. And then we also measured needle damage rates and intensity. As you can see in these 2 pictures here, here's my wrinkly, crusty hand holding a very drought-stricken root ball from a provenance. This is from the hottest temperature, around an average temperature of 31 degrees. And this is very small for a 2-year-old seedling. And then over here, we have a very dead-looking seedling. It's really been affected by drought. So it was important to record incidences of drought and see how that, or incidences of damage and see how that related to temperatures in drought. And then we also looked at why did it happen. So we could see on the broad scale picture, okay, so there's differences in biomass levels, growth occurred more in certain temperatures. But we want to say, why did that happen? So we looked at more like photosynthetic needle level measurements. We first looked at water use efficiency, and we related that to the drought intensity. So water use efficiency is the ratio of water emitted from the needles to the amount of carbon produced, or the amount of photosynthate produced. So by having a higher water use efficiency ratio, plants require less water to produce the same amount of carbon, which you can imagine would be very useful in a drought situation where you still need to produce carbon to stay alive, but you want to maintain as much water as possible. And then we also looked at the photosynthetic response to temperature. And the questions we were trying to address with this was, how do photosynthetic rates vary between provenances? And how do they vary between temperature treatments? So we measured these measurements with this device here, the LiCore 6800. It measured the gas exchange. So we put a little seedling inside the chamber here. I hope you can see my mouse. I think you can. So yeah, we inserted the seedling here into this gas exchange chamber. And we measured the results with, or we could see the results in this, this device here. And then this is just a neat little picture of a needle cross section that I took. We use this to accurately determine the gas exchange measurements per unit. So now we get into the more interesting component, which are the results. So first off, damage and growth, which I think is the most important for considering management in your woodlots. So we notice here that there are 3 different panels in this figure, one being the probability of severe needle damage, the total biomass of the seedling, so that's roots and shoots combined, and then the root to shoot ratio, how the root to shoot ratio changes per provenance over these average daily temperatures, as you can see on the x-axis here. And I just want to point out too that this black line here represents the average daily temperature of fir in its southern limits in eastern Canada currently, and this green line represents climate change projections for that same region by 2100. So we should notice the first result here is that small roots and biomass, as you can see in these lower 2 panels, are associated with severe needle damage. That's 75% needle damage or browning and above in these hotter conditions of starting around, say, 27 degrees on average. And another interesting thing too is that there are limited growth declines far past climate change projections. So this is for the hottest region in the Eastern Canadian region by 2100. And these growth declines start to occur, you know, and that by an average of say 5 to 6 degrees above the projections for climate change. And then the last point I want to make here is that there's significant growth differences between the northern and southern provinces across the board for each panel. For the first one here, the southern one seems to be damaged less in hotter scenarios compared to the two northern provinces and the mid-southern province. The biomass differences are very small between the 2 southern provinces and the northern provinces as well. And root to shoot ratio is also quite different. We'll get into temperature response curves. So this is more of the why did these results occur from the previous figure. Also, well, I guess I'll get into the figure first, where on the y-axis you have the carbon assimilation rate, so that can just be said as the rate of photosynthesis. And on the x-axis here, we have the chamber temperature within that LiCore machine that I was showing you. So as you can see here, all of the seedlings, regardless of provenance or treatment level, treatment level being cold, the southern provenance grown in the cold condition, or the northern provenance grown in a hot condition on this legend here. So regardless of the conditions they were grown in or the provenance, all of the seedlings seem to show a photosynthetic plasticity to the environment. As you can see here, if you take the southern provenance and grow it in a very cold condition, its photosynthesis is not only very much lower than the other 2 treatment types, so southern intermediate here and the southern hot here, it also photosynthesizes best at around 22.5 degrees, where you take the same provenance and put it in a very hot situation, such as an average of 31 degrees, and you'll find that its optimal temperature is not only much higher, or its photosynthesis is not only much higher, but its optimum photosynthetic temperature is at a much higher temperature as well. So that means that it can photosynthesize better in hotter conditions, which is very advantageous for a seedling. And we can see that there isn't much of a difference between provenances in terms of the response to temperature and treatment type until we get into the hot conditions, where you can see here, the southern provenance is able to photosynthesize much more at hotter temperatures than the northern provenance. And the northern provenance seems to be able to, it seems to fall off at around an average daily temperature of 31 degrees. So this increased photosynthesis in hotter chambers may be correlated. We haven't done that yet, but it may help explain some of these results we see here, where there's less damage here for this southern provenance, and we can also see how all of the seedlings respond best to an average daily temperature of 23 to 26 degrees. So I was going to go over the drought response, but I don't think I have enough time. If you have any questions about that, I do have the slides in the back that I can bring up in the question period. So now we're getting into the discussion, and this is how these results may affect your woodlot management or just your woodlot in general. The growth of balsam fir seedlings may increase with climate change. May, and I bolded that for a reason. There are many factors. I'm not including this as a very controlled experiment. There are some differences amongst the provenances, but they're not very significant. They may be significant for other reasons, but for management of your woodlot, this doesn't mean, these results don't indicate that you should be planting seedlings from southern, balsam fir seedlings from southern Nova Scotia into your woodlot in northern New Brunswick. And mortality rates are also not a concern under current projections. As you saw in that first figure I showed you, mortality rates aren't projected to start really getting bad until you get to average temperatures of around 27 degrees, which is just not going to be happening in most of New Brunswick. And that's in growing in favorable conditions where there's adequate moisture. So that means that high rates of fir regeneration and stocking should be considered in management planning for the foreseeable future. In figure 13 here, it's quite a nightmare for some of us. I don't know about all of you guys, but you know, quite a grim sight here. Just hiking through this would be quite a nightmare. But we may be experiencing this site for years to come based on these initial results. And there are also some other things to consider. As with all research, there's some caveats. This is not representative of climate response in other life stages of balsam fir. So that these results do not imply that we'll be seeing more of these large balsam firs, you know, minus the crack, of course. But we're not going to be seeing more of these based on my results. It's just saying that this is just for the seedling stage. My seedlings, again, were grown in favorable moisture conditions, so these results may vary depending on the site quality and moisture quality in your woodlot. These growth increases may not be as severe when you compare these growth increases in temperate species. So these temperate species may benefit from global warming more, climate change more, meaning that there'll be an increase in competition for balsam fir and therefore a decreased growth. And finally, if there's not temperature that's limiting the southern range of the fir, then there's anecdotal evidence suggesting that biotic factors may be the reasons for the southern boundary limit of balsam fir. You know, if you could take southern fir and bring them down south to the Carolina, and they would grow hypothetically very well, but they're not growing there. So there's anecdotal evidence saying that an increase of pathogens and insects and increased competition is some of the reasons as to why fir is limited to where it's at. So in conclusion, in case you missed some of my slides, my experiment aimed to see balsam fir seedling response to climate change because of the results that we'd seen from Anthony Taylor and other model projections about how it will respond to climate change. So we saw that balsam fir seedlings show positive response and strong adaptive capacity to climate change in this region. But significant growth differences between provenances, but this is not relevant for woodlot management. And our results suggest that the future declines of abundance may very well happen, but they're probably not limited or linked, to the impacts of climate on the regenerative phase of balsam fir. So with that, further research should be conducted to incorporate age and population-specific growth responses, because we've proven here that it is important. So we should incorporate age and population-specific growth responses for balsam fir and for many other species in the Eastern Canadian forest region. Thank you very much for listening. For further inquiries, I've included my email here. I'd be happy to answer any questions that you guys have regarding my research. And with that, I'll probably stop sharing my screen here, if I can figure that out.
Perfect, Jake. That was great. I suspect you'll have quite a few questions about balsam fir coming up this afternoon.
Awesome. I'm looking forward to it.
So next up, we have Joe Collier. Joe is master student at UMB, examining the impact of climate, stand, and site variables upon regenerating balsam fir in the Acadian forest region, under the guidance of Dr. David McLean and his research committee. Despite being in the weeds of data analysis, Joe finds this project to be very exciting. While many climate projections examine mature trees, regenerating trees in their response to climate remains an area that is less examined. And at present, Joe is finishing up the analysis of his field data and consolidating his results into his thesis. Prior to enrolling at UMB, Joe lived in the Yukon, worked for the Yukon U Research Center, where he still works remotely, part-time, as a project coordinator. Joe's currently living in Halifax when not working diligently on his completing his degree. Joe enjoys writing and playing music and getting outside to enjoy the outdoors. Joe, take it away.
Hey, thank you, Patricia. I'll just get my screen set up here. Okay, I think everyone can see that. Hi, everyone. Yeah, thanks for the intro there, Patricia. My name is Joe Collier. I'm a Master's in Science and Forestry student at UMB. My supervisor is David McLean, and I'm fortunate to have Dr. Loic, Orangeville, and Dr. Anthony Taylor on my committee as well. Yeah, really enjoyed all of the talks so far. There's definitely going to be a little bit of overlap in mine, but also some interesting new facets of information about regeneration. So,
Joe, you're not sharing.
Oh, not sharing?
Nope.
Oh, fantastic. Okay. Oh, I forgot to hit the button. There we go.
I do that a lot. Now we can see.
Okay. Okay, excellent. So yeah, my master's is focused on examining fir regeneration along a climatic gradient in Atlantic Canada. And I'm going to get into the why of that right now. I think there's been a few different iterations of this figure shown so far. But this is quite similar to a figure that Jacob showed in his past presentation. And basically this figure shows 3 different projections based on 3 different climate scenarios for the Acadian forest region from 2010 to 2100. At the bottom, I've highlighted balsam fir, and we can see that in all of the figures, balsam fir is expected to suffer a decline. So sort of where my research comes into this is that while these figures are looking to the future and to the year 2100, we should be able to see some evidence of this decline happening already. While it may be more difficult to see it in the overstory, some of these changes will be manifest in the understory and in the regeneration layer. So that's where my research comes in. So I'll quickly review my research objectives here before outlining my study and a little bit of information about balsam fir, and then going over where I'm at with my results and some early conclusions. But in a nutshell, my research objectives are to determine the significance of climate variables, which can include climate moisture index, minimum winter temperatures, growing degree days, precipitation, and mean summer temperature, as factors affecting balsam fir regeneration, abundance, and growth. And 2, to determine the relationship of harvesting and climate upon balsam fir regeneration, abundance, and growth. From my overview of the literature so far, I've come to a couple hypotheses regarding these objectives, which I'm in the process of testing. First off is along a climatic gradient ranging from northern New Brunswick to southern Nova Scotia, I predict that balsam fir regeneration abundance and height increment will decline as growing degree days increase and climate moisture index decreases. And secondly, I predict that these impacts will be more pronounced in areas that have experienced clear cutting, largely due to the fact that clear cutting removes the buffer layer of the overstory, so regenerating seedlings are more exposed to these changes in the climate. As you can tell, these are pretty broad stroke hypotheses, and I think one of the big takeaways from not only my presentation today, but many others, is that context is very dependent here, and we're working with models that can sort of work on a macro scale, but there are so many small factors to take into account at the individual scale too. Next up, I want to talk about the study region. This plays a pivotal role in my study, and I think it's important to understand the rationale for why I've set up the study this way. As I mentioned before on my first slide showing the climate projections, those projections are interested in how climate changes over time. Given that I'm trying to finish this master's this year and I don't want to be studying the same area for 10 years, we've substituted time for space here. So we've tried to represent a change in climate over a north-south gradient, which you can see here in my mean annual temperature gradient on the left, and then the mean annual precipitation gradient on the right. I've shown these two maps here because we know that both of these climate parameters are particularly influential upon balsam fir regeneration. While mean annual temperature can promote balsam fir growth, it's very context dependent. It can depend upon climate moisture index, other competitive species around the substrate of the soil. Mean annual precipitation is somewhat more straightforward. There seems to be quite a strong positive correlation between the regeneration of balsam fir seedlings in terms of density and in terms of growth and mean annual precipitation. My study is roughly divided into 3 climate zones represented by the different colors in my legend there. So white represents kind of the cooler climate zone, largely in the New Brunswick Highlands there. The pink represents kind of the middle zone, and finally the burgundy represents the sort of warmer area. So across my study area, we sampled 60 plots, half of which were in mature sites and half of which were in immature sites that had been recently harvested. When I say recently, it could range back to 15 years. So it's all relative there. I'll talk a little bit more about the methods for sampling now. So as I mentioned, we sampled 60 plots. This was in the summer of 2020, from July to September. We made sure to complete the study before leaves really started dropping from the trees, as that would affect canopy cover. We had within each of those 3 climate zones, 10 plots within natural stands, and 10 plots within recently harvested stands. One thing I was particularly cognizant of is, given that you know, this is quite a massive geographic area, and there's going to be a lot of variability in terms of landscape from northern New Brunswick to Nova Scotia. So while doing a study that in terms of geography versus in terms of time, it's really no substitute. It's certainly a compromise. I tried my best to sort of minimize variation between study sites. So prior to field work, I spent a fair amount of time going through and selecting permanent sample plot sites, which Loic touched on briefly, but essentially these are set up by each respective provincial department, and forestry workers will go to these permanent sample plots from year to year, measuring all of the trees in those sites, updating the database. So with those databases, I was able to select sites that were quite similar in terms of balsam fir composition and balsam fir basal area. Also, I was able to select sites that had fairly similar attributes in terms of when they were harvested. So with the site selection out of the way, I'm going to talk a little bit about the sampling that we did and the key variables that we measured based off my literature review. Okay, so I'll talk about the sampling here. Here's a picture of my field assistants suffering as they try to count all of the balsam fir seedlings within this quadrat. There's Leo on the left there, and he had the enviable job of counting all of the balsam fir seedlings in this 2 by 2 meter quadrat. This one doesn't seem so bad, as most of the seedlings are slightly larger in height, but in some of them there could have been hundreds to thousands of very small seedlings in these quadrats. James is diligently taking notes as Leo shouts out numbers of seedlings to him. In addition to counting balsam fir seedlings, we also counted seedlings of other species, as I was interested in competitor species and how those ranged across the study region. In addition to counting seedlings, we also measured the cover percentage of substrate. So if you look at this photo, you can see it's largely broadleaf litter, as well as the cover percentage of other vegetation. We're quite interested in how some vegetation might compete with balsam fir, such as mountain maple and raspberry, for instance. And a lot of the literature suggests that balsam fir prefers certain substrates over others. For instance, broadleaf litter, while high in nutrients, as the leaves fall in the fall, they can smother seedlings and kill them. So wanted to record these. And finally, we recorded canopy cover as well. Of course, canopy cover plays a huge role in balsam fir abundance and growth. We know that balsam fir is a fairly shade-tolerant tree, and its life strategy is such that it can stay within the undergrowth for many years until a gap opening allows it to grow. But nonetheless, literature shows that increase in light will perhaps unsurprisingly increase balsam fir height increment and radial increment. So I measured canopy cover using hemispherical photography at each of the 12 quadrats within our site, using different exposure settings, and then processing everything using a piece of software called ImageJ to determine the gap percent. So for my results, I've broken this down into a few different sections. We'll start off first with just the plot summaries. So just going over some of the data that we collected from the plots without really performing much in terms of analyses, just to see some of the patterns that present themselves right away. I'll then talk about some of the multiple linear regression models that I've created. And then from there, talk about some of the key relationships to further expand and talk about. And then kind of where I'm at from there in terms of plotting some of the interactions that have been deemed significant from my models. So first up is this beautiful series of graphs from Excel. I'll quickly explain what these graphs are showing and then talk about some of the trends. First off, 6 graphs here. These are representing my study regions going from left to right. We have northern New Brunswick, southern New Brunswick, and then Nova Scotia. So sort of representing that north to south climate gradient. And then from top to bottom, we have the natural sites. and then the recently harvested sites on the bottom. One of the first things that sort of springs up when you look at these figures is the blue color, which represents balsam fir seedlings. Pretty much far and away, it dominates all of these figures, which is great. It means that my site selection was somewhat successful in finding sites where balsam fir seedlings were abundant and dominated as we predicted they would. Next up, it's quite interesting to notice the change in height classes. So the y-axis of these figures represent height classes, with 0 representing germinates and 6 representing fairly tall seedlings. So you can see it's not a great life being a balsam fir seedling. In the top left figure here, you can see out of the 350 germinates, chances are low that most will survive to be about 5 centimeters and get into that height class 1. So there's quite a large die-off of seedlings. Most are quite unsuccessful, and very few make it to the stages where they could be considered established, which you would see in the later height classes where there's much less fluctuation. A few other interesting trends here. Northern New Brunswick far and away had the highest number of seedlings, especially in the natural sites. Furthermore, yeah, natural sites across the board generally had more seedlings than the cut sites, with some of the Nova Scotia cut sites in particular having very few seedlings. And I'll speak about that a little bit more when we look at the canopy cover in the next slide. So again, I thought it was important to bring up just some of the variability introduced by the canopy cover. It was my intention when I was selecting sites, and I was sort of thinking to myself that the canopy cover would be much lower in the cut sites. But of course, as anyone knows who has entered a cut site that's 10 to 15 years old, that is absolutely not the case. Intolerant hardwoods kind of dominate the canopy. However, well, that is kind of what we see here with the canopy cover being quite high, almost at 90% in some of the sites. But some of the sort of different successional pathways that we saw upon the site being clear cut definitely showed up as well. So some of the Nova Scotia sites here represented in gray had very low canopy cover and were quite open, sort of consisting of open areas dominated largely by bracken fern. So there was a lot of variability in canopy cover, and I think it's really important to highlight that here because it's going to come up in my analyses further on. With that, I'll get into the analyses. I'm fully aware that it's quite jarring to look at a table like this in a PowerPoint presentation. So I'm going to just go through some of the more interesting points of this table that I've highlighted and briefly talk about some of the patterns that are evident here before looking at some of the key relationships. First off, when looking at this table, I'll briefly explain what it's showing. So this is a multiple linear regression summary, and it's examining my 3 dependent variables. So in these top 3 columns here, we have balsam fir density, balsam fir height increment, and balsam fir radial increment. These are compared against a whole slew of independent variables, which were used to create models for each of these dependent variables along the top here. There's a few that I wanted to talk about that I've highlighted here today. And then I'll talk about the overall models for each of these dependent variables. One thing worth mentioning for the purposes of this presentation and how we're looking at this today, estimate here we can interpret somewhat as a slope. So with a positive number indicating a positive correlation, negative is a negative correlation, and the larger number means a stronger or a steeper relationship. So with that said, in terms of balsam fir density, precipitation had quite a strong positive correlation. It's quite a steep and positive slope there, which was in line with my hypothesis. Again, we saw that for the other dependent variable, height increment, and less so for the radial increment. Similarly, frost-free period lined up with my hypotheses as well. As frost-free period increased, the number of days without frost, we saw a decrease in balsam fir density across the study region. This variable wasn't included in the models for height increment or radial increment. And then some of the site variables, such as the substrate and the dry moss cover, had quite a strong impact upon balsam fir density. Another thing worth noting is that while it's important to look at these variables on their own, you know, all of these plots represent a very complex, nuanced system that is constantly interacting with each other. So it's really important to look at how these variables interact with each other too. I've performed a bunch of sort of preliminary and selection analyses to determine which variables to include and how they interact with each other. And I've included some of these here. So for instance, dry moss cover and canopy cover, we see it's the estimate here is less important than the fact that it's a significant variable to be included in this model. And this basically means that as canopy cover changes, whether the relationship is positive or negative with balsam fir density with respect to dry moss, that will change, which is to be expected perhaps as some substrates have better qualities for retaining water than others. And maybe when the canopy is open, that substrate is more prone to dry out. But you can see that including all of these interaction terms, it's very easy to get a complicated model quite fast. A couple other points I want to note really quickly about this. As Loic mentioned in the previous presentation, yeah, this is absolutely a model, and it's in no way is it a perfect simulation of what's going on at the plot level. We can see down here at the R² adjusted, which sort of talks about the overall fit of the model and its probability of predicting correctly. It's relatively low. So in terms of density, it has about a 36% chance of accurately predicting. It goes up somewhat for the height increment and radial increment, being able to predict 51 and 50% of the time. Again, those numbers should be taken with a grain of salt too, but it shows that we're dealing with a very complex system, and it's just a model and an exercise. With that said, it's a little bit easier to see some of these key relationships as they're graphed like this. So this panel of figures represents, similar to my 3 columns before, I have balsam fir density in this column on the left, balsam fir height increment in the middle, and balsam fir radial increment on the right here. Each of these is compared against 3 of the most significant variables that we saw from the analyses. So frost-free period for these figures on the top, precipitation in the middle, canopy cover on the bottom. It's quite clear to see here the effect that frost-free period has on balsam fir density. Oh, I should mention as well, we have all of the seedlings in their respective height classes represented here. So you can see that frost-free period, negative impact upon density across all of the height classes, a little bit more nuanced in terms of height increment with some differences in terms of height classes and a fairly subtle slope. And again, for radial increment. Precipitation, we see an increase in density across all of the height classes with some more pronounced than others. Relatively small effect on both height increment and radial increment. Canopy cover, for the most part, as canopy cover increases and the forest becomes more shaded, seedlings density decreases, with the exception of the smaller height class here. Similarly, both height increment and radial increment will decrease too. So this is one indication of sort of the interaction of height upon these independent variables here. So that takes me to my next slide, which, yeah, basically this is sort of where I'm at in my study right now. There's several more sort of complex interaction terms that I want to chart and investigate more thoroughly. Some of those being the site status, and again, height and canopy cover, and examining those against some of those other independent variables. Which leads me to my concluding remarks. So I think despite the fact that this is still a work in progress, from the analyses so far, it seems that, yeah, some of those hypotheses, while they're certainly talking about the broad strokes, there seem to be some significant relationships that align with the my hypotheses. One of the challenges with building this model is many of the climate variables I was working with are closely correlated with each other, something I had to be quite cognizant of when I was selecting variables for my models. Again, speaking about that huge margin of young balsam fir seedlings that we would see sort of dying in the germinate stage, it was important to establish a threshold of ecological significance based on survival rate. So I excluded those germinates from my analyses as they added too much variation. Most of them were going to die anyways. Again, another point is that, yeah, despite best efforts to select recently harvested sites with kind of uniform canopy cover, that wasn't the case in reality. Canopy cover was highly variable, so all the more important to include it as an interaction term. And yeah, that's it. So kind of still on the broad strokes here, but it's looking promising, and I'm excited to continue with it. Real quickly, just some acknowledgements. A big thank you to my supervisor and my committee. They've been fantastic throughout this process. And thanks to my research assistants pictured there, Leo and James, for all of their hard work. And thanks to Faith at UNB for all of the help in the logistics of sorting out my fieldwork, especially during COVID. And some references there for anyone interested, and questions, which we'll do at the end. That's my email. Thank you.
Thank you, Joe. That was very interesting. Next up, we have the last of our researchers today before we go to a panel, Storm Robinson Campbell. Storm started her career by completing a forestry technician diploma at Fleming College in Lindsay, Ontario, where she earned the Canadian Institute of Forestry's Gold Medal Award. She then went on to attain a postgraduate certificate in Geographic Information Systems Cartographic Specialist. In 2020, she earned a Bachelor of Science in Forestry at the University of New Brunswick. Storm's master's thesis will assess the growth variation in red spruce in response to extreme weather events, such as late spring frost, early fall frost, winter thaws, and drought by assessing tree ring data. Her experiment will also include testing the frost hardiness of red spruce provenances from throughout the species range. When not working on her thesis, she mostly spends her time supporting her son play hockey as a goaltender. She also likes yoga, reading, hiking, and kayaking. Storm, take it away. Oh, you're still muted. There you go.
Yep, there we go. Thank you for the introduction. I'll start by attempting to share my screen and see how that goes.
Perfect.
Is it there now?
It is.
Okay, perfect. Okay. How do I minimize that? Okay, there we go. So yes, I'm Storm, and as well as Dr. Loic d'Orangeville, who you've met as my supervisor, I also have Dr. Neil Peterson from Harvard Forest and Dr. Charles Bork from UNB on my committee. So I'm studying the effects of climate anomalies and frost hardiness on the growth of red spruce. My main focus is frost events such as winter thaw freeze events and late spring frost impacts. And the implications for this research will fall within the scope of assisted species migration, which you were also introduced to earlier, and looking at that as an adaptation strategy in climate change. So first I'll introduce a little bit of background on conifer frost hardiness, and then we'll talk about assisted migration briefly because we've already discussed it a little. Next, I'll introduce the risks to red spruce in particular as a species. And finally, I'll present and discuss some initial results from both my fall frost hardiness experiments and from tree ring analysis looking at past climate events. So conifer frost hardiness is different. It's unlike deciduous species because they retain their needles in winter to take advantage of photosynthesis when the temperatures allow them to do so. So this strategy requires freezing prevention mechanisms to protect the needles and other living tissue. Sorry. So cold hardening or acclimation is stimulated by a reduction in both light and temperature. So the figure here shows 3 species of conifers and their frost hardiness levels over time. Cold acclimation would occur in the fall as the trees adapt to cold temperatures. And then you can see each species reaches a different depth of hardiness in the winter. And then they deacclimate in the spring at the start of the growing season. So problems tend to arise with this pattern when the depth of temperature surpasses the depth of cold hardiness. This tends to occur midwinter during a midwinter thaw when trees are tricked into deacclimating early. Or similarly, this happens in the spring when a late frost occurs past the start of the growing season. Haven't spoken all day, so I'm a little, okay. So you can see here that traits such as frost hardiness tend to vary between tree species, but it's also known to vary within populations of the same species, dependent on the climate in which their genetics come from. So just really briefly, since we've already introduced assisted migration, I'll just say that it's a management adaptation strategy meant to assist trees in their shift northward as temperatures rise during climate change. So several Canadian provinces, including BC and Ontario, have already moved ahead with their plans to incorporate assisted migration into seed transfer. And so as you can see in the maps here surrounding the Great Lakes, they have highlighted in orange seed sources on the top photo and those seed deployment areas in the bottom photo. So that's one way they're moving ahead. So some issues to consider when you're moving provenances north is frost hardiness. So we wonder if they can maintain their growth with a higher risk of frost. There isn't much for diversity in these scattered southern populations of red spruce. As you can see, they're quite small, and this is due to a glacial refugia. So all that's left is really high elevation red spruce populations. So there's not a lot of genetic diversity here to choose from or to experiment with like you can with, say, white spruce. So red spruce is unique in that sense. And so we're asking, is there a trade-off between growth and frost hardiness in a species with such low genetic diversity and a small population size? And how significant is that trade-off? So red spruce is a keystone species of the Acadian forest, and it's valuable in industry. So it's a long-lived, slow-growing conifer. And red spruce is at risk due to high sensitivity to temperature fluctuations. There's a lot of research on that. And as I mentioned, a low genetic diversity and a small population size. And multiple studies have shown it experiencing rapid dehardening. in the winter and spring when compared with balsam fir, for example, also with other spruces as well. So as Jesse mentioned earlier on, this species is well known to have winter injury and frost hardiness issues. Red spruce experienced a historic growth decline from the mid-1960s through the 2000s, and winter cold injury was identified as one of the causes for the decline. Acid rain was a known contributor to decreased frost hardiness in this species. So we're wondering, is now that the pollution is gone and the Clean Air Act has been amended and introduced, is this changing? Is this different? Is the negative effects of frost hardiness still applicable? Or is the recent recovery of the species proving that winter injury is no longer a problem? Just some of the questions we're thinking about. So this leads us to my first research question. Does the climate or the temperature and the location of the seed origin of these trees have an impact on their cold tolerance? So our approach to answer this is to use provenance trials. We induce frost damage on mature trees that have seed sources from throughout the species range. And then we compare the responses of warm adapted and cold adapted populations. So the map here shows the provenances or the seed origins as orange diamonds, and the trial site is located at the Red Star at the Acadia Research Forest, close to Fredericton here. And this is where our samples are harvested from. So using climate data such as mean annual temperature and winter temperature led me to a preliminary divide of cold adapted provenances, including New Brunswick, Quebec, and Maine, and then warm adapted provenances, including New Hampshire and North Carolina. And that left Nova Scotia and Massachusetts somewhere in the middle. And you might see there's some overlap there, but that's mostly due to elevation. So that brings me into my methods. So to measure frost hardiness specifically, we sample red spruce shoots from 60-year-old trees from 7 different provenances across the species range. In the photo here, you can see the tall pole pruners we needed to use to get as high in the canopy as possible. And we do this during the fall, winter, and spring. So in all kinds of weather conditions and road conditions. So that was a great time. So after each harvest, we freeze samples to a target temperature using a liquid nitrogen controlled rate freezer. We start at 4 degrees and reduce the temperature by 6 degrees per hour until it reaches the target. It's held there for 3 hours and then brought slowly back up to 4 degrees. Then we measure conductivity to determine the electrolyte leakage, which measures the extent of damage that was incurred due to the intracellular breakdown of cells that happens from frost damage. Then the samples are fully cooked to release all of the electrolytes possible, and then they're remeasured for maximum damage. This produces a relative conductivity value for the samples, which is equal to freeze-treated conductivity over maximum conductivity. So now that you understand the basic methods, I'll discuss what we've done so far. So we started off last spring with some experimental trials, and we learned all kinds of amazing things, such as the storage effects on the samples, and also that trying to determine a single threshold for the exact frost hardiness on 7 different dates on many different provenances was really next to impossible. We ran tests at 17 different test temperatures, and we realized we needed to go back to the drawing board. So it was basically developing this method kind of from scratch in our lab. So, so once the methods were perfected, we began our first official experiments just this past fall. So in autumn, we did 5 field collections every 2 weeks between September and November, which represented the earliest frost date for our region. All of the provenances were tested at -10 and -30 degrees Celsius to mimic a mild and extreme test temperature or frost temperature, plus a 4-degree control, which was never frozen. This totaled 504 samples, which were then measured 5 times after freezing them to develop a rate of electrolyte leakage over time. And this totaled 2,520 measurements. So this figure here shows all of the relative conductivity results just from the first harvest date, so just from one date, on September 21st. Each point's a replicate sample taken from an individual tree, and each figure is a different provenance. So the x-axis is the time after freezing the sample, and you can see that the model fits the data quite well. And these curves ended up defining what's known as the rate of electrolyte leakage for each provenance. So this ended up producing a single value that represents the damage incurred to each provenance, which is much more comparable value than the traditional relative conductivity value measured at some arbitrary time. So, some researchers, they want to know what is the frost hardiness threshold for this particular stand or this particular forest, and you can easily find that. But in order to compare different provenances, it made a lot more sense for us to pick one value and then see how those provenances responded. So this is how we did that. So that brings me to my autumn results. Here we see the date in months on the x-axis from September to December, with each series of points one of the harvest dates. The electrolyte leakage rate in percent leakage per day is on the y-axis, which represents the extent of the damage incurred on each provenance during the -30 test. So on September 21st, in early fall, we can see a clear divide between the provenances, with the two warm adapted provenances, North Carolina and New Hampshire, in pink and yellow, experiencing the highest rate of damage, meaning they are the two least frost hardy provenances. In the background, you can see the daily temperature minimums for the same dates, just for your reference, in the gray line. So after September 21st, we see a large drop in temperature. And then on October 5th, we see the rates of damage remain the highest in the warm adapted provenances, with some increase in the rate of damage for the middle provenances, with a clear low rate of damage still for Maine and New Brunswick. On October 19th, if you look at the blue provenance, that's Quebec, and its rate of damage makes a really unique pattern. So maybe I'll just explain this without the arrows. So if you see here, the light blue is Quebec, and it the rate increases at this time, and then it decreases a little bit, but then it rapidly drops, and all of a sudden in November the rate of damage is almost nothing. So that kind of represents that this particular provenance is incurring a lot more damage earlier on in the season, and then suddenly it becomes frost hardy. Whereas when you compare that with the Maine provenance in purple, it's more of a level, gradual rate of damage throughout the whole season. So it's just that I'm basically just trying to explain that there's many, many different patterns that we can glean from this data. Yeah, so that was finishing that thought. And so the pattern seen in the first 4 dates before it reaches the end of November, when all the provenances, of course, become fully acclimated at some point when you get closer to the winter. But if you look at these first 4 dates, there is a significant difference between the warm and the cold climate classes, with a p-value of 0.03. And so as expected in mid-November, all the provenances finally reach cold acclimation, but it's just, my hypothesis was exactly dead on what we thought we would see here. And so far in the fall, it's looking like that's what's happening. There is some genetic differences in the response of these provenances. So the other half of my research, which is also ongoing, is looking into past events and what impact frost events may have had on the growth of the same trees. So kind of a continuation or another way of looking at Jesse's research. So by looking at the growth rings of the trees that he collected, we can find years with significant growth declines, and these are called pointer years. So in the figure here, we can see a very simple example of negative pointer years for 8 different provenances. This is for the same site at Acadia Research Forest, but I'm also doing this on 4 other sites as well that Jesse was also took course from. So this is just one example, but the y-axis is the seed origin and the x-axis is the year. A white triangle represents a weak reduction in growth, orange is a strong decline, and red is an extreme decline. The provenances are ordered so that the cold adapted provenances are on top and the warm ones are on the bottom. So we want to know what's going on here. Are these growth reductions occurring due to climate or frost events? And do these events impact the trees differently depending on their climate of origin? Sorry, I missed my points there, but that's okay. So here you can see some of the events that were found. The events in 1987 and 88. Most of them are winter thaw-freeze events with one late spring frost in 99. But the 87 and 88 winter thaw-freeze, they reduced growth in almost all of the provinces, whereas the late spring frost, it only made a decline in Maine and North Carolina. And then, in 2000, we had both a winter thaw freeze and a spring frost, and we saw a strong growth decline just in the North Carolina province. So really, this is ongoing research. I haven't drawn any conclusions yet, but it presents more questions, such as, does the compiling effect of multiple events have more of an impact than a single severe event? Or is the rapid return to cold temperatures? Or is it the number of growing degree days above 4 degrees that makes the most severe impact when it comes to then a frost event happening? So this brings us back to my initial question. Is there a significant trade-off between growth and frost hardiness that can be seen in red spruce? So in conclusion, warm adapted provenances are experiencing significantly higher rates of damage than cold adapted provenances when moved north. And warm adapted provenances may have experienced greater growth declines than cold adapted provenances during frost events in the past. And if trees are more frost hardy, they likely won't grow as much. But the faster growing trees from warm adapted populations may not be the solution for assisted migration. Maybe sticking with local seed sources for this species would be the best idea. We just don't know yet. And finally, and I think most importantly, these methods can easily be adapted to look at frost impacts on seedlings and on other species, including deciduous species known for sensitivity to frost, such as yellow birch, for example. And that's all I have. Thank you for listening. There's my contact information.
I like your picture.
Thank
Thank you, Storm. That was great.
you.
So everyone, we're going to take a quick 15-minute break before we start the panel discussion, so everyone can go get a drink and rest their voices for a few minutes. So please do come back at 3:30 and we will begin again. Thanks. I'll just ask our panelists to please turn on their cameras when they're ready, please. And I'd like to welcome everybody back for a bit of a Q&A session, panel discussion with all of our speakers from today. We welcome back Kristen Elton and Shelby Heath from this morning from the New Brunswick Invasive Species Council, and Loic Dorneville, who's been here all day, and Jesse Morris dos Santos had to return to his job. Gigi is unwell, so unfortunately not here today. But we do have James Broome, Jacob Raven, Joe Collier, Storm Robinson. We did have a few questions while you were presenting earlier, so if it's okay, we'll start with those. So the first one from Jenna is a broad question for the panel. Is there any research being done on the relationship between fungal networks and the health and adaptability in New Brunswick forests?
Not that I know of.
Not that you've heard?
No. I know of nice work being done in the US and in Quebec about this, but I haven't heard of work being done here. Yeah, I mean, in some way, looking at, overall stand health sort of integrates all the finer scale processes and interactions taking place in that stand. But it is a valuable question. I mean, trees are being planted and grown in nurseries, are inoculated with certain fungi to help them grow. And there's some interesting results as to how certain types of mycorrhizae can help trees cope with certain droughts, for instance, and certain levels of stress.
Let's start. So our next question is an interesting one. Denica asks, well, she has a question about buying woodlots that in their present conditions and in the future. She's seeing more spruce fir previous plantations for sale, which is to be expected, rather than woodlots that have a lot of diversity on them. So she's looking for like a small scale harvesting to help with house and hobby farm construction. But she's nervous to purchase any of the abundant spruce and fir dominated woodlots because of the losses projected due to climate change. Do you guys think that she should be hesitant in that? Or is it maybe easier to adapt a woodlot to climate change and not as risky to buy those sites as she's thinking?
Anyone else wants to chime in? Jacob, go ahead.
Yeah, I mean, as any response should start off with, is that it really does depend on the age, the site, the age of the species and the site quality, right? If there's high moisture, low moisture. And then also the harvesting history of the woodlot. Those are all factors you should consider when you buy a woodlot. If it's a small scale woodlot with a primary softwood dominant component, there are ways in which you can manage your woodlot in a pretty sustainable manner that will make it more climate resilient, and also you can use management techniques that can help convert it to a more climate tolerant stand composition. But it all depends on the time scale and the resources you're willing to invest into managing it to this, or kind of pushing it to this proper species composition. So, you can be planting, you can be doing thinning to allow for more water and resources for each stem. So I'd say it depends, but there are things you can do to prevent the losses from climate change.
I also think you kind of hit the nail on the head there in terms, you talk about timeline too, right? I'm not a climate researcher, but are you looking like, what is this a woodlot that you're expecting to want to use for the next 50 years, 100 years? What what is the timeline for those changes that are going to be occurring here in New Brunswick for a small scale woodlot? And then I mean also, what is this something you're hoping to pass down generations, or is this something that you might be, I guess, from what your long-term goal is with it, and if it's just something that you want to utilize while you're living there, and you're not thinking of selling it down the road, that kind of thing, right? Like, I guess we talk about the value of the land and what you're specifically valuing, and how those line up with the timeline of the projected climate change shifts.
I would add just a small thing, is that in terms of stands collapsing, these types of things, in general, what we expect is that the change in composition, the fact that fir spruce becomes maladapted, is going to follow major disturbances. So if the stand is healthy, if it's not overstocked, or then there's still good chances they will cope with some level of warming. And if you're closely managing it, then I think you can really help it transition to more climate adapted species. So I wouldn't refrain from buying a spruce fir stand if it seems healthy and well managed, and if you're ready to spend some time to to get it prepared and adapted. As soon as trees die and you see openings and windrows, you can enter the stand and adapt it and make the right decisions. Then it's perfectly fine thing to do to buy one.
Good answers. I think this question is specifically towards Storm. In what way is red spruce a keystone species in the Acadian forest?
Yeah, so I actually answered Tony in text, but I can kind of summarize what I thought. So it's well known that red spruce is very characteristic of the Acadian forest. I think that my main question would be, if we didn't have red spruce, would it still be called the Acadian forest? So in that sense, it's characteristic of it. As far as it being an actual keystone species for the ecosystem, if it was eliminated because it's such a long-lived and late successional conifer, I believe that it would be taken over by shorter-lived species, potentially, or just other things that aren't characteristic of the Acadian forest. So if your forest is being invaded by other things that aren't your main characteristic species, then your ecosystem as you know it is going to fall apart. And that's the definition of a keystone. So I don't know if that answers your question, but, or maybe you don't agree. I'd love to hear your thoughts. I don't know.
Tony did add a note. He's looking for an ecological perspective. Yes, it's a characteristic, but I'm not quite sure.
I feel like you're digging a little bit, Tony, but we can change the word from keystone species to a characteristic species, if that'll make you feel better. I'm fine with that. I'm not an ecologist, so maybe an ecologist would be able to answer that question better.
I can jump in. I guess, yeah, keystone species really is one that is going to, if it was removed from the environment, have a large ecological impact. So say, or, you know, influence their environment in some way. So beaver is a really good example. They come in and they impact and they create wetlands with their kind of ecological engineers. So they are really at a kind of higher level of ecological impact, you could call it, in terms of being a species. That's my 2 cents, and I went to university for, so hopefully my degree was worth something. I don't know.
Yeah, I agree. And I do believe that my first explanation kind of did allude to that idea that if you removed red spruce from the ecosystem, you would be left with a forest that's not the forest that you recognized before. So it would have an ecological impact on at least the trees, if they count for anything.
It is one of the most shade tolerant species of trees we have, and one of the oldest growing species we have. So it does tend to be very representative of these old growth stands that we find in the Acadian forest region, that we don't find in like west of here or south. It's quite unique to our ecosystem, that type of species, and it has a very small range. So it's only found here in the Acadian forest, and only evolutionarily speaking, just only diverged from the black spruce species not so long ago. So it's quite a very young species, but very different from black spruce and very unique to this region.
Yeah, and part of my response to Tony was also that there's quite a hybridization with black spruce now. So not knowing how much that's actually impacted the black spruce population is also a question too.
Okay. Next question came from Anonymous. Due to the loss of insects and birds that disperse tree seeds, how much do you think this is going to impact the movement of trees naturally as they're trying to adapt their regions?
Again, I'm coming at this from the invasive species wildlife side, but usually when something leaves, something else comes in, takes its place. You know, so we might not, you know, we might see a decrease in some of the species that are currently playing a role in the spread of these tree species, but something could come in and replace it, and it could replace it and offer the same mechanisms of spread, or it could replace it and change how it's spread, you know, depending on how those new vectors or where those birds prefer to fly to. So a really big thing, it's hard with climate change. A lot of this is, we all know things are going to change, but we can't exactly predict exactly how in most cases. So that would be my 2 cents, is that yes, we might see a decrease in what we currently have, but something else will likely fill that gap. Nature does that whenever there is a gap. It's kind of like, it's like politics. Whenever there's a void, something will fill it. And the question is what will fill it, and how will whatever fills it change the way that those trees are dispersed? And I don't have an answer for that.
I guess I can just give a little bit more of an invasive species perspective going off of that. As Kristen said, things will come in that will replace those species. So say we do have some tree loss, right? I talked about some of these understory plants, buckthorn, oriental bittersweet, that can kind of invade these niches or openings in the canopy. And they have a lot of, these very aggressive growth tendencies. They have the berries, they have the, rapidly spreading roots. So it's kind of, there's more opportunities for that kind of transmission. Like we see birds moving around berries of buckthorn and things like that. And it's, again, not as good in terms of nutrition for the birds, but they are using them and moving them around. So there might be more cases of those kind of transmissions around forests as well. So again, things we don't really know until climate change and all these things happen.
Another one of those things that's very hard to predict. Next question is from Jean Daniel. How do you think the forestry industry in New Brunswick will react to the decrease of softwood productivity and anticipated with climate change? Is there any interest in initiating research on the role of the evolving forests under the climate change context and their role in regulating the hydrology within the New Brunswick watersheds?
I think we need an economist on this panel.
So let's start with the first part. Are you optimistic or pessimistic, I guess, as to how quickly the forest industry in New Brunswick will react to the decrease of softwood productivity anticipated with climate change?
I think they're already reacting in a way, not because necessarily of climate change, but just because of markets and needs for hardwood fiber instead of softwood fiber. So like I was visiting some regions of northern New Brunswick, and the foresters were telling me, like, poplar is getting more popular, and veneer and yellow birch is getting more traction lately, and sugar maple is getting much more traction than softwood. We're making more money with hardwoods and softwoods lately. And they're just going with that, So I don't think such a long-term climate change issue is really something that's on an operational level, something that's being considered. I think it's something that's increasingly important for strategic management for industry. I have some research projects going with JDI, and when I speak to them, they're very aware they're very concerned with this issue. But that doesn't mean that they're changing the way things are being done. But they're looking into it, if we can put it that way, Yeah. So I think there's always been changes in how the economy has worked, and so softwoods have been very popular for pulp for a long time. Now they're declining. Now it's like boxes for Amazon deliveries, which requires some other types of fibers. So they're shifting to other species, and I think they will do the same in the future. Luckily enough, there's lots of hardwoods that are naturally growing here, like red maple. We've got to find a way to use red maple.
I think that's a good point too. And I guess this is I think this is a sticking point with a lot of different industries and a lot of different issues that are linked to the environment, is that we all kind of have this big looming climate change is happening, but most of the decisions are made at a 5 to 10, 20-year scale, which unfortunately climate change always seems to just, the real impacts of people actually seeing climate change is just beyond that. So yeah, I guess, I can't comment. I'm not a forester. I can't comment on what the composition will be and the economics, but I think that unfortunately climate change is not something that is going to drastically impact the industry right now.
Looking into tree improvement. that's something they're doing right now, is looking into tree improvement, right? So rather than shifting to hardwood, they're looking more short term and saying, well, can we look at the drought effects of the spruce and see if they can grow more even under some climate change scenarios and things like that. So looking at the growth of their own SPF type lumber and pulp industry, you know, that's kind of where they're looking at short term, I think.
Jacob, did you have something to add?
Yeah, I was just going to say that my philosophy of about this, my approach to this is that we have to sort of test their material. Like if industry is going with boreal softwoods as they are right now, we got to see how sustainable this approach is under climate change and test it, you know, instead of trying to convince based on a more, you know, long-term, vague, general trajectory, you know, where we know that, you know, hardwood, you know, temperate species are likely to be more to win this climate change war, but this is a long term. This is hard to be very operational and be very precise and specific as to like, okay, what's the growth rate going to be like, you know, and what's the mortality rates going to be like, and so what's the loss going to be, and with a 40-year rotation age, you know, what can I expect in terms of losses of and cost, you know? So you got to sort of test it on the ground and do all sorts of experiments to really show them numbers, and then they'll come to their own conclusions based on empirical data, you know. But it's hard to convince when we just have some models. It's just not as easy for everyone to grasp, which is understandable.
Yeah, we have a question. It's kind of aimed towards all of you doing research on balsam fir, but forests in general as well. Is there a way to mitigate the impacts of heavy snow loads and ice damage?
Sorry, I got distracted there. Do you mind just repeating that question again? I was just reading a question here, or a statement that Naren had made, but.
Is there a way to mitigate the impacts of heavy snow loads and ice damage?
On balsam fir is what you're saying?
Oh, that was seemed to be the species they'd like. I guess that's what they have a lot of.
Ice
But
and
forests in general, I guess. I mean,
I don't know if I can chime in at this point, because so we had, you know, this 2018 sudden fir mortality event. It did seem to coincide with this heavy April snow depth. Now that's a climate anomaly, not necessarily linked to climate change. And really, from my presentation, it was a lot of the drought effect that was really driving the mortality, and that snow depth was really kind of, you know, maybe the anomaly that linked these historic events and the 2018 events together. But I think you just got to be cautious, at least from my presentation, to think that it's snow depth only. It's a lot to do with drought as well. So yeah. I don't know if that answers it really, but it's just my perspective based on my research. I guess, you know, we just have to keep an eye on all these anomalies that are happening, and you know, when trees are dying in your woodlands. And you know, it's great to have today's conference, and you woodlot owners are, you know, really crucial to the forest industry. You know, you're the boots on the ground. You see this mortality happening in your woodlands, and then you can feed that information back to us, you know, scientists, and you know, hopefully we can answer the questions you come up with. So.
just going through what we have here. And don't forget that you can use the raise your hand button if you have a question, and we can unmute you as well. We have quite a chat conversation about economics at the moment going on in the chat window.
I have a question for the researchers.
Absolutely.
Yes, we there's a lot of work happening out of the Northeast US looking at the intersection of climate change and invasive species. It's called the Regional Invasive Species and Climate Change Network, I believe, and they've done assessments looking at what areas are going to be more susceptible to invasive species based on predicted climate models. And I'm wondering if you know of any similar work that has been done like that here in New Brunswick, and if not, would you be interested?
Is it a sort of a climate envelope approach based on the climate space of the current insects and how this climate space will just move north with
I
climate
believe so.
warming?
Yeah.
Yeah. There must have been, probably including New Brunswick as part of the Eastern Canada initiative. There's probably, I've seen some maps on that, but I haven't heard of anything specific to New Brunswick.
Unfortunately, a lot of their analysis stops right at the US border. And we look at what they've done in Maine and just try to extrapolate beyond that. I mean, one of the big things that we struggle with is that we don't have a lot of invasive species data here in New Brunswick. So, there's some efforts for certain species, but for the most part, we're just kind of going based on, we know it's here, we know it's there, but we don't know abundance. We don't know a lot of we don't have a lot of quantitative data showing the impacts here in New Brunswick, which makes it hard to then apply some form of analysis to predict what areas are going to be harder hit as our climate shifts. But that is something that we are very interested in learning more about and working with that group to see, what would be required in order to do some form of analysis like that. And I know that they're quite interested in extending that up because they do consider New Brunswick at least to be kind of like the tip right up there that they're just not including. And then there's a lot of different modeling in different groups that talk about, wildlife connectivity and that kind of thing down into Nova Scotia. But really we are kind of this gap. It's kind of like, we're the Maine of Canada to anybody in the US. And it's, there's a lot of stuff that we would just extend a little bit further that would be super beneficial to us. It's just trying to figure out how to get that work done.
Yeah, it's funny how a lot of research stops at the border. Insects, invasives, forest, it's the same in my field. It's really amazing how, I don't know, it's always half of the story. And even like our species, our tree species, at least they keep growing down the States, but we never incorporate that in the models, or at least it's very rare. It's only starting to be accounted for. So yeah, and I mean, these climate envelope models, they're not very complicated to run. I mean, James, you've done a lot of that stuff with your anomalies. Sure, that'd be interesting to work on. It's not something that's it's not too complicated. Yeah.
Good to know.
Yeah.
And that's one thing that I'll also put out to anybody who has a woodlot. Like we very much appreciate when people email us and say, here's what I have on my property, or, this is what I've noticed. Is it different? Is it something new in that area? Because, we're three people. We can't be everywhere. We don't have the knowledge. We don't have the intimate knowledge of an area. So we can go somewhere and it doesn't look any different to us, but somebody who, has been on that land for 10, 20 years can actually see those changes. And you're more likely to be able to say, hey, that plant wasn't there before, I've just noticed it, rather than us pointing it out. So, what we're really trying to do is get the word out to anybody, the public. We're really relying on citizen science, but to really take a closer look at what's around you, not just the trees, and submit that information to us, or to, even to the province, or just whoever, just to make sure that we're having that exchange of information between the people who actually are living it, and the one, us who are trying to do some of the work in the background. So we welcome any and all emails from people, and we will gladly help you try and ID stuff if you're not sure what you have.
I suspect that might become a popular offer.
I'll give you Shelby's email. So Shelby's
I was gonna say, it's already, don't worry, it's already happening, because yeah, it's great to get emails from people and start these conversations, right, about what their goals are and how we can maybe incorporate some of this stuff. Again, we don't have a ton of anecdotal evidence, and things in invasive species and forestry here in New Brunswick. So if there's any opportunity to, you know, do a small control plot and try some different control mechanisms, like I think it's just interesting that we are kind of on ground zero here for climate change, invasive species, forestry research. So it's exciting. Yeah, I think there's a lot of opportunity.
And there's also somewhat of a gap because a lot of the research that has happened in Canada is either Western Canada, it's on Ontario. So a lot of like best management practices come out of Ontario. And then you go to apply them here and it's like, well, we're significantly farther north. Like I will admit, I'm not from New Brunswick. And the first time I looked at a map and realized where Fredericton was, you know, in line with where you were in Ontario, it's a completely different area. So, you know, what might work in Southern Ontario to control buckthorn might not work here or vice versa. So those are a lot of the gaps that we have even for answering questions in New Brunswick, even when there is information out of Canada, is that it, you know, sometimes it applies and sometimes it doesn't.
I feel like that's the case. I feel like that's the case for some of the economic questions that are going on in the chat as well, you know, looking at, the only real choice that a lot of private lot owners have here is the clear cut right now. And I remember from doing the culminating project at UNB, it was the same. We were working with a private woodlot owner and it was the same deal. You know, clear cut really was the only viable economic option. And so coming from Ontario personally, I didn't understand that when I first came here. But then, you know, when you look at the volume and you know, there is quite a difference between the species and the volume that's being produced and whatnot. So I understand the frustration, but at the same time, you know, if those southern species are moving northward, well, maybe there is more to learn from Ontario, you know, moving forward. Who knows? Same goes for invasives, right?
There, if any of you need a new research topic after you finished your master's, I would suggest getting back in touch with the Invasive Species Council.
We've got lots of ideas if you want more
If
students
we had,
lined up.
if we had the funding, we could do every project. Trust me, we would have a great time. Yeah. If anyone has woodland angelica that they want to help me, I can go out and assess their woodland angelica, because we're, again, as Kristen said, writing the best management practice document for that, because it's one that we don't see a lot across different parts of Canada. So it's kind of a regional species that we don't have a ton of guidance on. So yeah, fun things that we will hopefully fill the void in the coming years.
That brings me to a question on seed collection. Those of you who have, pardon me, been doing experiments on seedlings, you get thousands of seeds from different areas. We've gotten a lot of questions lately, and yesterday in our panel discussion as well, people are wondering where they can get seeds. They don't, it's doesn't seem to be an easy thing for them to obtain.
Yeah.
Do you know of like seed collection agencies, I guess?
Well, yeah, there's we have in Fredericton the Canadian Tree Seed Center is located right here in New Brunswick. So it's for all the conservation of forest of tree seeds are stored for long-term right here in Fredericton, the Atlantic Forestry Center. So it's a federal agency, and it's a small group led by Donnie McPhee, a great guy, amazing Frisbee artist. And so they have, their mission is to store the genetic diversity of trees in the forms of seeds. Now, they will provide seeds for research, education, but it's not a commercial like seed business in any way. So, but then they have a lot of good connections with, and they know all the local players and seed collectors and provincial nurseries, etc. So it might be a nice, maybe they'll get their email boxes flooded after I say this, but it might be a good starting point to get to know where to collect seeds. So for instance, the Emerald Ash Borer, they've been running a big ash collection last year all across Canada to try to get as much ash seeds they could, grasp as much of genetic diversity of ash across the country. Yeah, and so they do a lot of that work, and I do collaborate with them. All the trees I'm growing for my projects are from the National Tree Seed Center, because every seed lot as well, you know, we have the coordinates, we know exactly where it's done, how it was done, the assessed germination success rates of every seed lot. They do some very excellent work for such a small group of people. It's quite amazing.
There's also, and I guess it depends if you're looking for seeds or if you're looking for seedlings, but I know it's one of the things that we've had an issue too, is trying to find native seeds for native plants, right? If somebody wants to do a native seed garden, flower garden, and most of the like pollinator packets you'll get, like you look on the back and most of them aren't native species. So we've had to look into this this issue as well, as where can we actually direct people to, and it's been tough to find, but there are a few native nurseries. There is one just outside of Fredericton, I believe, that it's just a single person. But the other thing I would recommend is maybe get in touch with your local watershed group, because a lot of the watershed groups do a lot of planting along rivers and creeks, and they tend to be, I know that they always try and source locally as they can. So that would be a good one to connect with, because they might be able to point you in the right direction as well.
Yeah, so, oh, sorry.
Go ahead. Go ahead.
I'll just say it before I forget, Liberty Tree Nursery is the one outside of Fredericton, if you're looking for more small scale. But yeah, great recommendation, Kristen. Again, lots of watershed associations looking for funding to do tree planting projects. So they may just need a property, or maybe if you're in their watershed, look to have just, you know, a project on your property. So definitely a good option. Sorry, go ahead.
No problem. I may be wrong in this, but I believe if you're looking for seed for, you know, the commercial management of your woodlot, and you want to be growing your own seedlings in bulk, I think you can get bulk improved seed or just normal orchard seed at local nurseries around New Brunswick. For example, the Island View Nursery near Fredericton. I believe you can get bulk seed.
I have a note from Kate Turner with the Nashwauk Watershed Association that yes.
Yes, thanks, Kate. Yes.
Native seed, yes.
Yeah, I was gonna say, Jesse is looking to expand his seed collection. He's mostly been doing his own seedling growing, but he is looking to expand. So I went and had a great conversation with him about maybe doing a native seed pack together. Maybe we can do something. We're trying to get some funding together for a garden wise program. So doing some behavior change around gardeners. We mentioned Japanese knotweed, some of these forest invaders, getting some awareness out there about how to properly dispose of those materials, manage them in your garden so that they're not impacting our forests. So hopefully, fingers crossed for funding on that. But yeah, he's a great guy. And yeah, Kate, that would be awesome. Nashwauk is great.
Now here is an interesting question. To all of you, but again, a lot of the balsam fir researchers, do you have any recommendations on how to mitigate a fir stand to something else? Or do you just purely focus on how they're doing, I guess?
So how do you convert a primarily fir dominated stand into something else?
Yep.
Kind of like building off of that previous question we addressed. Yeah, depends on the age of the fir too, and what you want to replace it with, right? So
we have a lot of foresters in New Brunswick who have quite a lot of balsam fir, and some that were growing them for Christmas trees to sell, of course, and they're starting to get out of that. So, well, especially some of the older ones that don't have anyone to pass that business on to. So they're perhaps looking to diversify, but considering the best conditions for balsam fir, what would be, I guess, an easy route to transition to something else?
Yeah, balsam fir takes over pretty much everywhere if you allow it to, right? it just seems to be a great generalist species. So when you're considering the transition of a fur dominated stand to, so this is already an established stand in this scenario. If you're considering the transition, you have to think about regeneration dynamics, species specific wise. So you don't want to be doing large clear cuts to get rid of those fur, because you're just going to probably be getting more poplar and more fur going up that way. So without seeing your stand, I'd recommend personally, you could do underplanting, you could do small patch cuts to allow for more kind of small scale disturbance species to come up, such as tolerant species, such as more of your spruces, potentially some hardwoods if you're in a good spot for that. But it would mostly be around planting and planting the desirable species and creating small scale openings, strip cuts, patch cuts, select cuts, just to foster the regeneration of more shade tolerant, desirable species.
Looks like we're starting to run out of questions. So last call, if anyone has any questions that they would like to address to the panel, feel free to either use the raise your hand button on the bottom of your screen and we can unmute you, or feel free to type it out in the chat or Q&A windows.
I just put in a link to our iNaturalist project that we have. It's a little shameless self-plug here. If anybody's looking to get an idea of what people have reported in their area in terms of different species, this is a really easy platform to use. This is just a project that we've put together to pull in a bunch of information, but you know, as I've mentioned, we have some gaps in understanding. So everyone, you know, a lot of people know about glossy buckthorn, but we're not exactly sure everywhere it is in the province or if there is a leading edge or anything like that. So even though it's one many people might be familiar with, we'd love to have more reports of it to get a better idea of where it is. A couple of the other different species Shelby mentioned, garlic mustard, oriental bittersweet, a lot of those understory growth plants. And then of course the pest, if you see emerald ash borer, hemlock woolly delegate, obviously you're getting on the phone with somebody. But for those, for the other ones, we definitely like to see as many reports as possible, because we just want to get a better idea of what and where is everything in the province.
I'll be sure to add those links onto our website as well.
Awesome, thanks.
Oh, Jean Daniel, okay. Is there any interest in initiating research on the role of the evolving forests under the climate change context and their role in regulating the hydrology within New Brunswick watersheds? Jean Daniel had kind of, he had a two-part question, which we really only addressed the first part about softwood. So
I'm not sure I understood the question here.
yeah, I think what he means, and Jean Daniel, please feel free to let me know if I'm wrong here, but no, that doesn't make sense either, actually.
Sorry, do you mean like in terms of how forests affect hydrology on a bigger scale, like watershed level? Or I'm not too sure. Yeah, because I mean, that would be, I'm not too sure New Brunswick specific.
I think
but
with the way that the forests are going to evolve, what role is that going to have on, say, the hydrology in watershed areas? Like the species composition is going to be changing, and also with not just timber-based trees, but also with invasive species as well. So,
well, yeah, I think we mentioned, right, there's a lot of impacts that we can't really see in terms of smaller scale, I just mentioned the earthworms, right? The invasive earthworms and how they can move up soil, right? Like even on a small scale, that if you had a large rain event, right, could impact hydrology. You'd have a large erosion event. We could have, you know, loss of soil and loss of root structures. So I guess there is, I just have an invasive species perspective. So please, if it's not relevant, but yeah, I just thought of that example is like, that would affect hydrology in some way, right? Because you're affecting soil composition and affecting, you know, the kind of structure of soil, but I'm not too sure in a larger forestry context. One of the forestry experts can take that one.
Oh, well, actually, Jean Daniel has raised his hand, so I'm just going to unmute. And we'll ask him to unmute so he can ask his question.
Yeah, thank you. Do you hear me? Are you
Yes, we
hearing
do.
me?
Yeah.
All right. Okay, thank you. It's because considering the impact of you know, the forest when it grows, and then it will change, and the species will change as well, and then the dynamic and the, you know, the local ecosystem will change as well. So it will impact the availability of water within the watershed. And already we see some example, like in the river, there is less water during summertime. And then considering the accumulated impact from forestry and so on. So there's a lot going on there. And the forest obviously has a big role as for the ecosystem. And it holds a big part of the area on the watershed. So if we change many variables, including the species on the land. So I'm interested in knowing if you're aware of any study in this regard, or if there may be some interest in doing studies like that.
There are many studies ongoing. I think that the reason we're not seeing them today is because most of them have to do with things like LiDAR and GIS and remote sensing. So a lot of those models involve looking at it through the lens of remote sensing. So watching what's happened in the past and modeling how that goes into the future. So it's just a different area, which I believe there are studies ongoing right now at UNB even, along with, I'm sure, other places, but it's just in a different lab under a different supervisor. So maybe Loic can touch on that a little more. He might have.
Well, just thinking of it, merci pour ta question, Jean-Daniel. In terms of species and amount of water being transpired by trees, for me, there's no obvious change that I can expect right away from climate change in terms of composition, shifting from conifers to hardwood or other species. You'll get more or less the same amounts of water being transpired. Now, if there's more drought, if there's less, if there's more mortality and losses of forest area, then you get an impact on the hydrology, right? The role of trees, faster, drainage and movement of water, these kind of things. But then it's a complicated question, because you got to add on top of that the geology, and New Brunswick is a complex study area for geology. So you'll have movements of water, will depend largely on the type of bedrock, and there's no obvious answer to your question. Unfortunately, it's really hard to say, to predict a general trend in the future, from my point of view, at least.
That is the frustrating part with many of the questions that we get.
Just on that, so Dr. Charles Bjork and Dr. Michelle Gray, they're both undertaking watershed type research at UNB. So it could be worth reaching out to them. I can add a link to the research areas at UNB in the chat.
Fantastic. We do have one more question here. Is there any ongoing research dealing with expected changes in non-commercial forest species? For example, vegetation with significance to wildlife, or non-commercial forestry projects, etc.
Well, I would say yes, yes and no. In a sense, there's a lot of funding that goes towards commercial species because of their abundance. They are dominant species, so they do have a larger impact when you think about the forest. I'm not saying it's true in all regards, though. But if you think of certain species, like red maple is not a commercial species in any way, but there's a lot of work being done with red maple because it's such an important species in other ways. But I'm not aware of, at least in my small world, I'm not aware of any studies on, you know, for instance, interesting mushrooms. I'm a big mushroom fan, but I don't know what's going to happen to my chanterelles in the future. I just hope they're going to stay there for a long time.
You could also look at a lot of the species at risk. There's the various species at risk that have been assessed would have some extensive research into those. There's usually one or two people in the country who are the experts on those. But if there's one that you're interested in, we can probably try and figure out who the appropriate person would be. I know there's I mean, I guess black ash, and ash is also a commercial species, but ash, butternut, there's my brain's not working anymore, but yes, there are certain species at risk that would also have an extensive amount of research, and the commercial ones, but it's those species in the middle, usually they kind of fall through the cracks, unfortunately.
That is very true.
I did some work with Jesse from the Liberty Tree Seed Center about bur oak. There's some work, but it's a small, you know, it has a small range around the river valley around Fredericton. It's not a important species in commercial ways. And we tried to get some money to try to better assess where the species current distribution is, and under climate change, it might be a species that might be interesting under warming. It is adapted to drier conditions, warmer conditions. If you look at the range of that species, it's kind of odd that you find it in the middle of New Brunswick. It's a disjunct range. The closest you see bur oak outside of the river valley here is in Maine, and then central US and etc. So, but there's not as much incentives at looking into these less commercially important species right now.
That's good. Well, we are getting to the end of our day. It's been a busy day. I know I've learned a lot, but I want to thank all of you for participating in the conference today. There's been some very interesting questions, and there are quite a few comments now in the chat about places where people can get seeds. So just to let everybody know, I will compile a list and add that to the MBFWO website for links and resources. So, okay, all right. So for today, I want to thank our panel for being a part of this. Great questions all around. And I'm going to pass things over to Susanna to end off the conference for today. Thank you, everyone.
Thank you.
Thanks.
Thanks.
Thanks, everybody.
Thanks you. Thanks, everybody. Thanks to all the speakers today and yesterday. Thank you to everybody that participated in the conference. We really appreciate having so many people come and listen. We hope you found the conference informative and that you've taken home a lot of information that you can use in the future. Thank you to Jim for the interpretation. We'd like to thank NRCan and Environmental Trust Fund for funding our project and the conference. I'd like to thank Louise Como and Megan DeGraff for the help in organizing the project and in coming up with the ideas about where we were going to start. When we started this project, it was like, okay, yeah, we know there's interest in climate change. Now what do we do? So thank you to them for their help in directing the course of this project. I personally think it has been an extremely successful project. The case studies will extend beyond the end of our funding from NRCan, which ends in the end of March. And I thank the 4 woodlot owners who have given up a piece of their property for us to do our case studies and to make those available to anybody that would like to go and look at them. There are QR codes at each site, so you will be able to find all the updated data on those sites. So I thank them for that. I want to thank the advisory committee that helped us to move this project forward. All the support we've had from NRCan, answering our project coordinators, our project people, leads, helping us with all our questions. So thank you to them. And a special thank you to Patricia, who was the project coordinator and without whom this project would certainly not have happened. And she was the one mainly responsible for this conference. So thank you for all the great work that she has put into this project. I would just encourage any of you and all of you to stay in touch with the Federation, follow us on Facebook and LinkedIn or on our webpage. You can sign up for our blog, and we will use that to continue to communicate and to send things out. And our webpage will be host all our YouTubes and all the information from this conference and from our projects. So, and always to let you know that we are always interested in what woodlot owners want, what woodlot owners need. So feel free to reach out with project ideas, things you would like us to look into. It's great to connect with the Invasive Species Council, because I think that's an important link, and to be linked up with the researchers as well, because that's how we get to move some of our questions forward. So I thank everybody for coming. I wish you all a good evening, and thanks again for being part of our conference.